Hey guys, hello.
Yeah. Welcome to the 2400 session. Uh, so far there's only four people here, which is eight people now, but it's better for you guys because you get more personal time with Autumn, and he can answer any questions you have. Mahima's gonna put a sign-in form, so if everyone can fill that out, that'd be great. So like no matter what you're here for, like a placement exam or just preparing for the exam, you can focus on whatever topic you want. From the from whatever Autumn's talking about today. And I'll also be like perusing the chat for any questions if you want to ask it there as well. Yeah, and just I guess a short intro again. I'm Johnny Beck. I'm the co-director for Bridge to Math, and I yeah, I'm a rising senior.
Hello, everyone. My name is Mahima. I'm a rising junior majoring in neuroscience. I'll be in the chat monitoring, but I'll mainly be sending out the sign-in form. So please make sure to fill that out before you leave so we can have everyone checked in. And then Adam.
Okay, yeah, okay. I guess we can get started. I guess to like start, like, are most people here for the placement exam? Could you just like raise like do the hand raise thing or something, or put it in chat or something? Um, or like, what's the what's the overall distribution? Because like that kind of will dictate what we focus on a little bit. Um, I guess I don't know. I can't see any hands raised. I'm gonna assume.
Yeah, they're typing in chat. They're
Oh,
mostly
they're in chat.
here
Okay,
for the placement exam.
okay. Placement. Okay. So it looks like most people are here for placement. So I'm gonna assume that you guys have a bit of knowledge of like the 1410 linear algebra stuff. We'll go over it a little bit quicker, but I do want to focus on like the later chapters because those are where things get like more complicated. So let's start. These notes are all posted and the solutions will be posted soon. Right now we'll go through the problem. So in this first session, we're going to talk about like the linear algebra section. And then hopefully in session two, we'll be able to go a little bit deeper into linear algebra and then talk about differential equations. Okay, so I'm assuming most of you are familiar. You have seen matrices before. They're just grids. Um, you don't denote a matrix by its size. So the number of, rows by the number of columns is 2 by 3. And if this is unfamiliar, by the way, if you have questions, like the best is if you can just unmute and ask and interrupt me, but also put them in chat. Feel free to do that because we don't have a lot of people, so there's like no need to like you can just interrupt me and unmute. Um, yeah, there's a few matrices that are important to know. The square matrix, which is, n by n, it looks like a square. And then the identity matrix has ones all along the diagonal and zeros everywhere else. So when we say the diagonal of a matrix, we're talking about the left to right diagonal. So technically there's like two, but we're talking about this one that goes from the top left to the bottom right. Um, a diagonal matrix is like kind of like the identity, except you're allowed to have other numbers on the diagonal. So it doesn't just have to be ones, but the only place you can have numbers is on a diagonal. So like a 3 by 3 diagonal matrix would look like, I don't know, 2, 1, 3, and then zeros everywhere else, right? Okay. Upper triangular means that you have your diagonal splitting the matrix into two, and then only these upper top right entries can be non-zero. Everything else needs to be zero. Lower triangular is the same thing, but opposite. Okay. This is all fairly straightforward. That's why I'm going through it pretty quick. You can just read the notes and like get these, terms in your head. The transpose of a matrix is an important operation. You flip the rows and the columns. So if our initial matrix is 1, 2, 3, 4, 5, 6, we take each row and write it as a column. So 1, 2, 3 as a row, we turn it into a column. 4, 5, 6 as a row, we turn it into a column. And you can see that here initially A is a 2 by 3 matrix, and then A transpose will be a 3 by 2 matrix. So the dimensions will flip. Okay. These two terms are important. Symmetric matrices. So like intuitively, a symmetric matrix is just like let's like the identity matrix is symmetric, right? Because you can imagine flipping it across the diagonal. your matrix, your entries don't change, right? Technically, the way we like to describe it is we say that A is equal to A transpose. So when I flip the rows and columns, my matrix doesn't change. That's a symmetric matrix. A skew symmetric matrix has a little bit more specific property. It says that your matrix is equal to the negative of its transpose. So let's like do it. Let's think of an example of a skew symmetric matrix. Like this, and like this, and like this. So this would be a skew symmetric matrix, right? Because if this is A, right, let's take A transpose, right? So what we do is we take each column, each row, 0, 1, and write it as a column. And each row, negative 1, 0, and write it as a column. And you can see that A and A transpose are negatives of each other. So you negate every single element. And so we see that A equals negative A transpose. Okay. They'll never really ask you like in a problem, give me an example of a skew symmetric matrix, but like the phrase could come up in a problem. It could be like do something with the skew symmetric matrices, so they'll assume that you know what that term means. Okay, another important thing about a matrix is its trace. So that's when you just add all the elements along the diagonal. So it's very straightforward, right? Here, if A is 2, 5, 0, 4, you find the diagonal 2, 4, and add up the elements. That's the trace. Okay, matrix arithmetic, I hope adding and subtracting matrices is relatively straightforward. You add each element. Multiplying by a scalar, you scale each element. So C3 multiplies each element in this matrix. And then multiplying by another matrix is a little bit trickier. Let's just go through how it works with this example. The way it works is if you're multiplying two matrices. So here, we're multiplying a 2 by 3 matrix, right? Multiplied with a 3 by 2 matrix. Okay, and the only way for matrix multiplication to work is if these dimensions align. So the number of columns in the first matrix must equal the number of rows in the second matrix. Okay, the way you figure out what the output is if you have a 2 by 3 times a 3 by 2, you sort of like imagine ignoring these threes, and then the output will be a 2 by 2 matrix. Okay, so the output of this matrix will be a 2 by 2 matrix when we do the multiplication. Now, how do we actually do the multiplication? We go through every row and every column, and we take the dot product. So the dot product is given right here, right? If you have the dot product of, let's say, A, B, C dotted with D, E, F, you do the first entry times the first entry, plus the second entry times the second entry, plus the third times the third. So let's do the example out here. 1, 2, 3. So we're going to do each row dotted with each column. So we do the first row dotted with the first column. So 1, 2, 3, dotted with 1, 2, 3 is going to be 1 times 1 is 1, plus 2 times 2 is 4, plus 3 times 3 is 9. So we get whatever, 14. And that would go in the top right. Okay, so it's bad. The 14 would go here in the top right. Similarly, to do the entry to the right, we take the first row and we dot it with the second column. And we can go through that example like that. There's also going to be examples we're going to do, so I won't spend time on that on the arithmetic. All right. So here are a few practice problems. This first one should be fairly straightforward. Think about it for a sec. What would you do? You'd take the rows. So you take 1, 2, 6 as a row and write it as a column, and then 3, 0, 1 and write it as a column. Okay. Problem 2. Take a second and think about this. I'll give like a minute. This is a more interesting problem. It's saying describe the trace of a skew symmetric matrix. So it's saying in general, remember, let's recall what skew symmetric means. My pen wants to work. Give me a sec. Okay. So skew symmetric means that the matrix is equal to the negative of its transpose. And we're interested in the trace of it. So take a second to think about that. These are like questions that are kind of testing your understanding more of what these concepts mean. So I would start by just thinking about what skew symmetric matrices have to look like, right? If I have a matrix like 2, 1, negative 1, 1, or whatever, right? This can never be skew symmetric because if this is my matrix A and I take its transpose, notice that, right? 2, negative 1, 1, when I transposed it, these diagonal elements are always the same, right? When I take the transpose, the diagonal doesn't change. But we need A to equal negative A transpose. So that will never happen if there are numbers along the diagonal, right? We need, like, for example, this number here to be the negative of this number here. So 2 is never going to equal negative 2. The only way for A and A transpose to be negatives of each other is if you put zeros along the diagonal. And hopefully that explanation made sense, right? So now if I have a matrix like, okay, 0, 0, I don't know, -1, that's I already did that example, 0, 0, 2, -2, right? This is a skew symmetric matrix because if this is A, when I do A transpose, notice how, yes, the diagonal stays the same, right? But they are still negatives of each other because 0 equals -0. Okay, so when they're asking for describing the trace, remember the trace of a skew symmetric matrix, so the trace of A is going to be add up the diagonals, so 0 plus 0, so it's going to be 0. Okay. All right. Nice. And then 3, I don't know if we want to go through, maybe we just do, okay, let's come back to this if we have time. This is just saying find a bunch of matrix products. So let's just first make sure, we'll do an example of seeing if they actually exist. So let's see if AB exists. So A times B, A is 2 by 3, B is 2 by 3. So these elements do not match, so this one does not exist, right? A multiplied by C, let's do that one, right? A is 2 by 3, and C is 3 by 2. Okay, nice. These match, so this does exist, and the output is going to be a 2 by 2 matrix. Okay. All right. And you can obviously go through the calculations, and you can check your answers when we post the solutions. Okay. Any questions on that chapter in the chat? I'll give like a few, basically after every chapter, I'll just wait a few seconds for questions. I think that chapter is fairly straightforward. Okay, now we get into systems of equations using matrices. So this is kind of one of the advantages to using matrices. If you've all probably seen systems of equations, we have 3 variables, 3 equations, right? We can represent this in terms of matrix multiplication. So if you can see, this left representation and this right representation are the exact same. Because if I take the right and I do the matrix multiplication, the first row multiplied by the first column, when I take the dot product, it's going to say, okay, 5x plus 10y plus 5z equals 15. And so we're basically rewriting our system of equations. Okay, so basically any system of equations can be represented in the form a times some vector x equals some vector b, where A is this matrix here, right? This vector x is the vector with your variables in it, okay? And the vector b is like the right side of the equation. So this part. Okay, something you're gonna see come up more commonly is that instead of using like x, y's, and z's, we're sometimes gonna have more than 3 variables. So we tend to just use like x1, x2, x3. So we can like extend that to like as many variables as we want without using many more letters than we want to use. Okay. Now, how do we solve? So how do we solve a system like this using matrices, right? There's 2 ways. We're first going to talk about Gaussian elimination. So what this means is we take our matrix A, the initial matrix, and we call it, we form this thing called the augmented matrix, which means you take A, put it on the left side, and you take B and put it on the right side. And you sort of put a line to distinguish the two. Okay, then we want to do this technique called row reduction. So the idea is we eventually want to turn this matrix A here into row reduced echelon form. Okay, so here are some examples of row reduced echelon forms. What row reduced echelon form is, let's go through the 4 things. The first non-zero entry in each row is 1. Okay, so that means that if you look at this example right here, right, there's no numbers below here. That's 0, right? The non-zero entry in each row is 1. Okay. The other thing is these 4 things, like, yes, they are there. They can kind of get confusing. You honestly just learn to like identify row reduced echelon form just by looking at it. The key thing is that even if you have a 1, right, you're not allowed to have a 1 here and a 0 here because these 1s are in the same column. So as you go down rows, your 1s should be kind of shifted over no matter what. If you can see here, right, your 1's here. As you go down a row, your 1 is shifted over. Okay. Similar idea. This one's fine. It's fine to have some numbers here because remember, the leading 1 is all we care about, right? The other important thing is that if you have a row of zeros, okay, they're always at the bottom. So we should move any rows of zeros to the bottom, okay? And so how do we go from, let's say, this original matrix form up here to one of these reduced forms? We do this thing called row reduction, okay? So row reduction, there are three operations we can do to this matrix to turn it into this one. So the first thing we can do is swap rows. So we could say like, okay, I'm going to turn this into, instead of 5, 10, 5, 15, I'm going to put the 5, 10, 5, 15 here, and then I'm going to swap it with the 3, 12, -9. So that's one way of doing it, right? You just take these two rows and swap them. Okay. The other thing you can do, the second thing you can do is multiply any row by any constant you want. So fraction, whole number, whatever. I could, for example, say, okay, I want this 5, 10, 5, 15. I want to divide everything by 5 and turn it into 1, 2, 1, 3, or whatever. Okay. And the third one, the most usually useful one, is to add a scaled row to another row. So this means that, okay, so let's call this guy row 1, this guy row 2, and this guy row 3. So the way we usually write this in notation is we'll write row 1 equals, let's say, row 1 plus 2 row 2. Okay, so what we're saying is we're going to replace row 1. Every term is going to be the term in row 1 plus 2 times row 2. So let's see, row 1 plus 2 times row 2. So 2 times row 2 is going to look like 6, 24, -18, 18, right? With a line in between. And then we're just going to take that and add it to row 1. So we're going to do 6 plus 5 equals 11. 10 plus 24 equals 34. 5 minus 18 is -13. And 15 plus 18 is 33. And then this is going to become our new row 1. Okay? All three of these operations are allowed. And that's how we're going to go from original form to row reduced echelon form. So let's do an example. I think next we're going to see an example of it happening. Okay, so let's walk through step by step what's going on here. So we're looking to actually find row reduced echelon form for our example here, right? The way you want to go about this is, remember, the ideal goal is to turn this matrix right here into the identity matrix. Okay, it won't always happen, but the goal is to get something like this. Okay, so the way I like to approach row reduction always is start with the top left, turn that into a 1, then go down and turn these two into zeros. Then turn this guy into a 1, and then go down and turn this guy into a 0, and then turn this guy into a 1. So that's like the steps. Honestly, row reduction is something that's sometimes overlooked. I think it's really fundamental, and to succeed on the placement test, you're gonna have to row reduce at one point or another. So make sure you're doing enough practice to like consistently be able to row reduce. So here, right, the first step, we make the leading entry in the first row. So we make this guy into a 1 by just dividing the whole row by 5. So this is actually an example I did. 5, 10, 5, 15. Divide by 5 becomes 1, 2, 1, 3. Okay, the next step is okay, this guy's a 1. Let's make both of these 0. So the question is, how can we make 3, 12, -9, 9? How can we turn this 3 into a 0? Well, we can use the third row operation we learned and said, okay, we're going to turn row 2 into row 2 minus 3 row 1. So basically, it's going to be 3, so row 2 minus 3 times row 1. And the reason we choose 3 and we choose row 1 is so that this entry here becomes a 0, right? Similarly here, we take this guy, 12, and we minus 3 times its corresponding entry in row 1, which is 2, and we get 6. So that's how we get 6 here. And then similarly, -12 and 0. And by the way, make sure you're doing these operations to the right side as well, because we're forming the augmented matrix. This is A and this is B, right? At the end of the day, this is going to tell us our solution. So make sure you're also doing it. You're treating the whole thing as like one big matrix almost. Okay. All right. What's the next step? Similar idea, right? Row 3 is row 3 minus 4 row 1, because we want to turn this 4 right here into a 0. Okay. Next, so then we have this, okay? Now, again, we've done our 1 here. We've done our zeros going down. The next thing we do is turn this guy into a 1. And that's simple. We just divide it by 6, right? So we divide by 6. Nice. Okay, looking good. We divide that whole row by 6. Now let's go down again. And now we need to make this 12 into a 0 because we have 1, 0, 0 here. We have a 1, and then we're looking to make this 12 into a 0. So we, take 12 times R2 and add them together, and then we end up like this, and then we finally divide this negative 16 to get out a 1. Okay, and if you can see the final form here, now we're in row reduced echelon form. Okay, so this matrix right here is an RREF. Okay, we could go a step further and turn these into zeros, but that's usually unnecessary because I'll show you why. Basically, if we turn this back, if we take this and turn this back into our system of equations, we get 1, 0, 5, 0, 1, negative 2, 0, 0, 1, right? Times x, y, z equals, and then the right side, 3, 0, 1 fourth. Okay, so if we now, one trick I'll always tell you is that we initially learn systems of equations by writing them out, right? We didn't learn them in this matrix form. So I always like to go back and like convert this back into, okay, x. So let's do the matrix multiplication. This row by this column, right? So 1 times x plus 0 times y plus 5 times z equals 3. Okay, that's our first equation. Let me scroll down a little bit. Oh, that doesn't work. Okay, let's try this again. Let me just try moving it. Move this up. Okay, that's not good either. Let's see if I can copy paste. Otherwise, I'll just rewrite it. Okay, let's rewrite it. We have space. All right, okay, let's just do it like this. So quickly. 1, 0, 5, 0, 1, negative 2, 0, 0, 1 times x, y, z equals 3, 0, 1 fourth. Okay, so we get x plus 5z equals 3. Okay, then we do the second row, 0x plus 1y, so 1y minus 2z equals 0. Great. And if you look at the third row, because the third row only has 0, 0, 1, x and y are eliminated, so it's 0x plus 0y plus 1z equals 1 fourth. So immediately we found z, right? Then we can go back up to the previous equation and find y, and then we also have z and we can find x like that. So from once you get to this stage, you can kind of just backtrack and solve the system in a much easier way. Or if you wanted, you could also go to the go all the way, reduce this all the way to the identity. But I don't feel that that's necessary sometimes. All right. So that's kind of the point. That's why we did all this row reduction, is that so we could easily spot out that, okay, z equals 1 fourth, right? If you look at this, there's no way you can solve z from that just by looking at that, right? So the idea is that this up here and this down here are equivalent. It's just one helps you see the solutions better. Okay, blah, blah. So here you can see that we actually went to the identity, but again, not entirely necessary. Okay. However, when you are in the identity, you can, or when you're in reduced row echelon form, we realize we can split our variables into two types. Okay, so so we have, let's go to our example up here. First, let's see how many variables we have here. So we have 3 variables total. Okay, we have pivot, we can split them into 2 types: pivot variables and free variables. Pivot variables are ones that are stuck, as in they have to take a certain value. Okay, so if you look at what this this matrix form is saying, it's saying, okay, x has to equal 7 fourths, right? Y has to equal 1/2, and z has to equal 1 fourth. So in this case, all 3 of our variables are pivot variables. So here we would have 3 pivot variables and 0 free variables. And you'll see what I mean in an example when we see a free variable. If you look down here, right, notice this row of zeros at the bottom, right? What is this saying? Again, one more time, let's just write it out in terms of matrix multiplication. So we'd have 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and then 0, 0, 0, 0. And then we'd have 4 variables. Let's do x1, x2, x3, x4. And then whatever. We have some constant here, constant here, constant here. But if this is 0 here, then look at what the last row multiplied by the first the column is telling you. So like, let's go step by step. So the first row times this column tells you that x1 has to equal c1. So x1 is fixed, right? The second row multiplied by this column tells you x2 has to equal c2, right? Do you see that? Because when you do this row dotted with this column, that's what comes out. Again, this one tells you x3 has to equal c3, and then this one tells you 0 has to equal 0. So if you notice here, that's always going to be true. And in our equations, we have no restriction on x4. So x1 has to be c1, x2 has to be c2, x3 has to be c3, but x4 can be whatever it wants. So that's why we say x4 would be free here. So in this example, right, we would have x4 be a free variable, and then x1 through x3 would be pivot variables because they're stuck in position. They can't move. They can't change. They have to take on one value only. Okay? The way you notice this is that if you have a column with a leading one, so if you notice that this column has a leading one, this column has a leading one, this column has a leading one, but this one doesn't, right? That's how you can tell that, okay, x1 is pivot, x2 is pivot, x3 is pivot, and then x4 is free. Okay. Again, this is something that you just learn how to notice the more practice problems you do. So let's see an example. Right, so this is exactly what I actually just wrote out. I shouldn't have written it out. I should have just used this. But we can see that what we're saying, the first three equations, right, tell us that x1 has to equal c1, x2 has to equal c2, and x3 has to equal c3. But the last one, there's no restriction on x4, right? It can be whatever it wants to be. Okay, so depending on your reduced row echelon form, we're gonna have three types of problems. In one problem, we're gonna get a unique solution for all our variables. So they're all gonna be one number. Like that's what we're used to seeing. That okay, x1 has to be this, x2 has to be this, and x3 has to be this. Another case is where you're gonna have no solutions for x1, x2, x3, and the third case is when you're gonna have infinite solutions. Okay, so let's look at each case. If you row reduce and you have a pivot in each column. So see, we have a pivot here because leading one in the column, pivot here, and pivot here. Also, you can just tell, right, that when we write this out, we're literally saying here that, okay, x1 has to equal 2, x2 has to equal 1, and x3 has to equal 3. So this is entirely, they're all pivots, and this is where we have one solution, okay, we have a unique solution for our system. Okay, let's look at this example, the no solution example, right? Notice how the reduced row echelon form does not have three pivots, right? It has a pivot here. Let me do it. We have a pivot here, a pivot here. So x1 and x2 are pivot variables, but x3 is a free variable because it doesn't have a leading one in it doesn't have only a one, and that one would have to be down here, right? And so x3 is free. However, notice that look at what this number is in this row. So if we write out the matrix multiplication, right, what we're saying is this, and if you look at the last row multiplied by this column, right, we get 0x1 plus 0x2 plus 0x3, so 0 equals 1, right, down here. And that's not possible. So no matter what x1, x2, and x3 are, they will not make this equation true. It's not possible. So this is when we have no solutions. So pretty much the way you should identify this is you should look, okay, if I have a row of zeros, okay, it's either going to be no solutions, right, which is where you have a number here, or if I have a row of zeros and another 0 here, then it's going to be infinitely many solutions. So let's go to that example. Okay, so that's the way you should classify. So your first case could be, oh, I don't even have a row of zeros. I have 0, 0, 1, so I'm good. I should have one solution. The second case would be, okay, when I row reduce my matrix, I end up with 0, 0, zeros here, right? There's one of two cases. If you have a number here, then you have no solutions. But if you have a 0 here, then we're going to get to infinitely many solutions. So this is what we saw before, right? What we do is we take the matrix, and we always, with writing infinite solutions, it always helps to multiply it out. So we take this matrix and turn it into its multiplied form, okay? As you can see, right, the last, this one, basically, let's see. Where am I? Right. This one sets a restriction on x1 and x3. This one sets a restriction on x2 and x3, but x3 itself can be whatever it wants, right? Because when we do this matrix multiplication here, we get 0x3 equals 0, right? And so there's no direct restriction on x3. So because of this, we recognize that x1 and x2 are pivot, and then x3 is free. So the first step is we write out our equations. The next step is we write all the pivot variables in terms of the free variables. So we're going to take this and we're going to write x1 equals 5 minus 2x3. So we're going to rewrite them in terms of the free variables. So x2 is going to equal 1 plus x3. And then obviously x3 can be whatever it wants. So we just let x3 equals x3. Okay? Now because x3 is free, we just give it an arbitrary value. Let's just say x3 is t. Okay? So imagine x3 is t here. That transforms our solution into this. Okay? So this is a solution, right? This is our answer. We've given that, okay, x1 is going to be 5 minus 2t. x2 is going to be 1 plus t. And what's t? Well, t is whatever x3 wants to be. So for example, if we choose t equals 0, then a solution is going to be x1 equals 5, x2 equals 1, and x3 equals 0. Right? So 5, 1, 0 is a solution. If we choose t equals 1, then we get another solution. We have infinitely many solutions. Okay, the other thing that's very common is to write this in vector form. Okay, so that's where you say, okay, an easier way to see this would be to write this as 5. So x1 equals 5 minus 2t, x2 equals 1 plus 1t, and then x3 equals 0 plus 1t. And as you can see, we can just add vectors. We can say this is equal to 5, 1, 0 plus negative 2, 1, 1 times t. Okay. All right. Any questions about these problems? Let me check the chat. Okay. I think it's okay so far. All right. Let's go to inverses. So remember, I said at the beginning, there's two ways of solving ax equals b. The first way is row reducing. The second way works when A is a square matrix. Okay. We are going to use these things called inverses. I'm sure a lot of you know about this, so I'll sort of skip over the intuition, but if you have ax equals b, the idea is if you have a times x equals b, right? What you can do is on the left side, basically we have this inverse matrix for a, where we know that a inverse times a is equal to a times a inverse, which is always equal to the identity matrix, right? So if we multiply by a inverse on the left here, right? We should get that this A inverse times A becomes the identity. So pretty much like 1 in the case of the matrix. And then we'll get that X equals to A inverse B. Okay, so that's our second way of solving it. We just have to figure out, okay, how do we find out this A inverse thing? Okay, so there's the good news is that for 2 by 2s it's very easy. There's an explicit formula. If this is your matrix A, B, C, D, you do 1 over AD minus BC. That has a name that's called the determinant. We'll talk about it in a little bit. And then you flip A and D and you make B and C negative. This is all fairly straightforward. I'm sure you guys have seen this. For 3 by 3 matrices, it's much more annoying. There's no formula, nice formula like this. What you have to do is you have to take your matrix and augment it with the identity. So you take your matrix A, put it on the left, and on the right side, you put the whole entire identity matrix. Then you do row reduction to turn, let's do a different color, to turn this matrix, okay, that was not it. To turn this matrix, okay, that was not it again. I don't know why I can't get my pen. Okay, this should be good. Okay, clear. And then, okay, sure. To turn this matrix into the identity matrix, and then whatever's left here is the inverse. Okay. There's two cases. If you're able to fully row reduce this to the identity, then this right here is the inverse. If you're not able to row reduce this to the identity, for example, if you end up with a row of zeros at the bottom, then there is no inverse of this matrix. And we'll get to more situations of that in later chapters. Okay. So let's do an example. If this is our matrix A, how do we find the inverse? We augment it with the identity. We do a bunch of row operations similar to how we did before, right? We've done row operations on A before in the previous problem. Blah, 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 blah. We end with the identity on the left here, and then what's left on the right is the inverse. Okay, do a few practice problems of these. I think we have some here. Yeah, we have some practice problems, so do those. Make sure you can get that consistently. Some inverse properties. Okay, A inverse equals A. This makes sense, right? If You take A and you inverse it, then you get A inverse, then you inverse it again, you get back A. So it's a repetitive process. Okay, this is important to know. There's a property that says that if I have two matrix and they're multiplied and I take their inverse, it's not equals to A inverse B inverse. You have to flip the order of them around. Okay, and you can test this out with examples, but at this point, let's just take it for granted. You just flip them around. Here are two more important ones. A transpose inverse equals A inverse transpose. So if I have a matrix A and I take its transpose and I take the inverse of that versus if I take A inverse and take the transpose of that, those are equivalent. The last one is that the determinant, and we haven't talked about determinant yet, but I'm sure a lot of you know what it is. The determinant of A inverse is equal 1 over the determinant of A. Okay, so these are some properties to keep in mind. They'll help solve problems in the future. So let's keep those in mind. Okay, this one, can we get could people in the chat go say yes or no whether we want to do this example of row reduction, like a simple row reduction example? Would it be helpful or should we skip over it for now? Skip, could skip. Skip. Okay. Sorry. Okay, I'll spend less time on this stuff. This is inverse again, same thing. We'll skip. Let's do this problem. This is a good example of more tricky tricky systems. Okay, so luckily we're already in reduced row echelon form, right? If you can see, the first leading entry is always a 1. Here, and here. Everything below is zeros, right? And all the ones come to the right of each other. There's no extra ones underneath, right? And so these numbers here being there, it's fine. They're a little bit ugly, whatever, but we can't really do anything about it. So this is row reduced nicely for us, okay? And let's see how many variables we have here, right? We have 1, 2, 3, 4, 5, 6 columns, so we have 6 variables. So let's write the general solution of the system. So what we're gonna have to do is we're gonna have to think about it okay, 1, 2, 0, 0, 1, 0, 0, 0, 1, 0, 2, 0, 0, 0, 0, 1, negative 1, 0, and then 0, 0, 0, 0, 0, 1, right? Times x1 through x6. Sorry, I'm writing on a tablet, so the handwriting is quite bad, but x5, x6, okay, equals 3, 2, 4, 5. Okay, so this is, remember, always in your head. This guy needs to turn into this guy, which needs to turn into, let's multiply it actually out and right. That's the only way you can really think about these. So let's multiply this out. So we get x1 plus 2x2, and then 0x3, 0x4 plus x5 equals 0. Okay, next one, 0x1, 0x2, 1x3, 0x4, 2x5 equals, oh, sorry, not equals 0, by the way, equals 3. My bad, right? Because this row times this column is going to equal this guy right here, not equals 0. So this should be equals 3. Okay, x3 plus 2x5 equals 2. 0, 0, 0, so x4 minus x5 equals 4, and then x6 equals 5. Okay, excellent. So they gave us right away, we know that x6 equals 5. So again, that tells us that, okay, x6 is definitely pivot. But if we also just look here, look, in the x6 row, the first thing is a leading one. So it's also a pivot, right? So there's many ways of seeing the same thing, and you should be able to connect the dots so you can feel confident. So let's see which variables are pivots. x1 seems to be a pivot. x2, no, because this is not a leading one. x3 is a pivot. X4 is a pivot. X5 is not, and X6 is a pivot. So it looks like our pivot variables are X1, X2, X1, X3, X4, X6, and then our free variables are X2 and X5. Okay, so now that we know that, we're going to write our pivot variables in terms of our free variables. So let's do that. So our pivot variables are X1, so we're going to write X1 in terms of X2 and X5. So 3 minus 2x2 minus x5. Okay. X3 equals 2 minus x5. X4 equals 4 plus x5. Also, remember, there's no explicit equation for x5. So we can say because x2 and x5 are themselves, right? In here, I'm just going to sneak x2 just equals x2. can be whatever it wants. X5 just equals X5. And sorry, I'm running a little out of space a little bit, but X6 equals 5 itself. So X6 actually equals 5. Let me see if I can fit that in. Okay. So pretty much now, this is a solution. Let's rewrite it with t's and other variables. So because we have two free variables, we're going to call x2, let's call this one s, and let's call x5 t. Okay, and let's rewrite our solution a bit cleaner so it's like legible. Sorry about that. So x1 equals 3 minus 2x2, which is 2s minus t. X2 equals s itself. So let's write it as like 0 minus 1s minus 0t. X3 is going to equal 2 minus x5. So that's 2 minus t, right? So 2 minus 0s minus t. X4 is going to equal 4 plus x5. So 4 plus 0s plus t. X5 is going to equal 0 plus 0s plus t, right? Oh, why did I do, sorry, x2 should not be minus 1s. It should be plus 1s because x2 should equal s. So this should be a positive 1 here. And this can be plus 0t as well. I don't know why I wrote that wrong. X2 should equal 0 plus 1s plus 0t. And then lastly, x6 is just equal to 5. And the reason I did all this and wrote it like this is so it's just very clear. When you want to turn it into vector form, right, the vector answer, I'll write it up here, write it here on the side. So answer is going to be your original vector, so 3, 0, 2, 4, 0, 5, plus, right, you do s times the first vector, so negative 2, 1, 0, 0, 0, 0, plus, and then this vector, negative 1, 0, negative 1, 1, 1, 0. Negative 1, 0, negative 1, 1, 1, 0 times t. Okay, so just like that. That's how you form the general solution. Okay. Any questions about that? If you have any, put them in the chat. Otherwise, we'll move on. This is like, you're gonna see this on the placement test, so make sure you can solve this. And it's not just that, like being able to solve a system like this will come up like as steps in other problems. So this like needs to be fundamental. Okay, this is very fundamental. Okay, determinants. Can you guys put in the chat? I don't want to waste time. How many of you know how to do determinants for 2x2s, 3x3s? Yeah. Yep. Skip, 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 skip. Okay, great. Excellent. Okay, so let's just do the example problems. One thing to know is that you need to know how row operations affect the determinants. So we'll quickly go over that. If you swap rows, your determinant goes from positive to negative. If you multiply a row by c, the determinant also scales by that c. And if you do the multiple of one row to another thing, that doesn't affect the determinant. Okay, here are some properties. The determinant of the identity is 1, obviously. Determinants multiply out. These properties are good to know. And you do get a cheat sheet, by the way, so it would not hurt to throw these on your cheat sheet for the placement exam. Okay, determinant of A transpose equals determinant of A. Actually, wait, I think. Okay, let's just quickly geometrically understand what determinants mean, because that's important to like understand this intuitively. If you have a determinant, a 2x2 matrix, okay, 2, 1, 1, 3, what the determinant says, right, is it says, okay, make a shape that has these vectors as its like sides. So 2 comma 1 will be, oopsies, 2 comma 1 will be my first. Let's make a grid. 1, 2. Let's make a grid. 1, 2, 3, 1, 2, 3, whatever. 2, 1 is my first vector here, and 1, 3 is my second vector here. So in this case, it's going to be like a parallelogram type thing. Okay, the area of this is equal to the determinant. So the area of this would be whatever. 2 times 3 is 6, minus 1 times 1 is 1 equals 5. So the area of this would be 5. In 3 dimensions, it extends to volume. Okay, and if you understand this, then it would make sense why a lot of these properties still hold, right? Like for example, the one I just talked about, where A transpose, you're just flipping the rows and the columns, but the actual shape itself is going to stay the same, right? Because it doesn't matter whether you go along the rows or along the columns, the volume of the shape is going to be the same. That's why the determinants are the same. Okay. Anyways, determinants of A inverse equals determinant of A inverse. So 1 over determinant of A. We talked about this one in the previous inverses chapter as well. And then this one's interesting. If you have a matrix A and you multiply the whole matrix by some constant C, then remember, if you have a matrix A, right, whatever, and you multiply it by C, then you're multiplying by C on this row, multiplying by C in this row, and in this row, right? And so when you take, or in every column, however you want to think about it, right? So when you take the volume of the shape that's made with these rows, it's going to be C times bigger in each dimension, right? So in like 3D, that means you're going to multiply by C, multiply by C, multiply by C again. So you're going to get C cubed bigger. So basically, depending on n, which is, sorry, I forgot to write it in the notes here, but n is the number of rows, right? That's how much you're going to scale your determinant by. Okay, anyways, kernel and rank, these are important words that come up a lot. And correct, yes, the determinant is related to the cross product, yes. The cross product is a determinant with your ijk vector and then the two vectors underneath. Very similar ideas. Okay, I'm assuming you guys have not seen these words before, so let's talk about this. These are very important words. So the kernel of a matrix is the set of all vectors such that A times X equals 0. So basically, to find the kernel, all you do, so you'll have a kernel of a matrix. So you have some matrix A, okay? The kernel of A, okay, is all vectors X such that A times X equals 0. So pretty much all you have to do is solve this equation or the system of equations, and then you can get X and you get your kernel. Okay. The kernel and the null space are the exact same thing. They're equivalent. And the number of vectors in the kernel is called the nullity. So I want to go back up to the example. I lost all the work we did. But if you remember in this example, right, we had, what did we have? We had like, okay, we had 3 vectors, I think, 2 or 3 vectors. So that would be your nullity, the number of vectors in your kernel, like the number of S's and T's, pretty much. Okay. The rank of a matrix is another important word. It's the number of non-zero rows you get after row reducing. Okay. So let's say I have a matrix that looks like this. Okay, 2, 1, 3, 2, 1, 3, and then 1, 1, 1. Okay, here's my matrix, right? If you row reduce this, you can clearly see that you're going to subtract rows 1 and 2 from each other. So you're going to end up with a row of 0 somewhere, and we always push it to the bottom, right? So in this case, if you row reduced and your matrix turned into something like this, right, where these are non-zero rows, you would say the rank of your matrix is 2. Okay. So that's the rank of a matrix, and the other thing is the kernel of a matrix. Okay. Now, what you should also realize is that another way you can think about rank is the number of pivot variables, right? Because when you row reduce, for every row of zeros you get here, right, that's going to be one each like loss to your rank. So each row that becomes 0 is you're losing a pivot. You're losing, you're turning a free variable into a pivot variable. Or sorry, a pivot variable into a free variable. Okay, so the rank is equivalent to, okay, the number of non-zero rows after your row reduce. It's also equivalent to the number of pivot variables, which are non-zero columns after your row reduce in a way. Okay, we know that the total number of variables we have equals the pivot variables plus the free variables. So from here, we know the pivot variables is the rank, right? The rank of the matrix. The free variables, the number of free variables we have is the nullity. Okay, so in the previous example, we had x2 was a free variable and x5 was a free variable. That's why we called them S and T. And so that's why we got 2 vectors out, right, in the kernel, right, in the null space. And so the number of free variables is equal to the nullity. Okay, it's the number of vectors you have in your kernel. Okay, so make the connection between those two words. So from here, right, we get that the rank nullity theorem, which is very important. It says the rank of a matrix plus the nullity of a matrix is equal to n, where n is the total number of columns, right, the number of variables in your matrix. Okay, there's always a good way to check your work. That if you have a matrix, you find its rank, you find its nullity, they should add up to the total number of variables or columns in that matrix. Okay. Um, here's where this sort of all connects together. Okay, so I'm gonna take 5 to 10 minutes to just talk about this, because if you understand this, then like all these terms will make more sense. Okay, so let's say we have a matrix A, okay, and the determinant is 0. Okay, immediately remember in the inverse formula, right? I always think about the 2D case, right, where the inverse formula is 1 over AD minus BC. So it's 1 over the determinant, right? So obviously, if the determinant is 0, then the inverse is not going to exist. So if the determinant is 0, right, the first thing that we say is that the inverse does not exist. Okay, now let's see how each one of these other things is all interconnected. The reduced row echelon form is not the identity. What that means, right? If the determinant of A is 0, that means let's say A is some nice matrix, right? A is some matrix with like, all numbers here. I'm just going to make an example. These numbers are going to make no sense, but imagine we have a number here, a matrix here, okay? Remember that we can do row operations on this matrix, right? We can turn it into a row reduced echelon form. And let's say, this is all an example. Let's say we get like 2, 1, 2, 4, whatever, 1, 0, 1, 0, and then 0, 0, 0. What we have said is that, look, we've taken A, we've done some row reductions, but now here the determinant of A is 0. And remember all those backtracking steps? If you start with 0, that's going to go back, that's going to go back here, that's going to go back here, and that's going to tell you that the original determinant of the original matrix right here is 0. So basically, the idea is that if you have a matrix and you row reduce it and you get a row of zeros, that means that your original determinant was also 0. Okay? So determinant of A is 0. But also, look, if you have a row of zeros at the bottom, then your reduced row echelon form is never going to be the identity. So that's how we know it's not going to be the identity. In a similar way, the rank of A is going to be less than the total number of columns, right? Here we have 3 variables, right? But because we know we're row reducing and getting a row of zeros, because the determinant is 0, we know the rank cannot be equal to 3. The rank has to be less than 3, because we're going to have at least one non-zero row. So here the rank would be 2, which is less than 3. Okay. Lastly, A has a kernel. Okay, many ways of thinking about this. If this is the reduced row echelon form of A, right? And if we do x1, x2, x3 equals 0, 0, 0, because remember, that's how we solve for the kernel. We say, okay, my matrix times some vector equals 0, ax equals 0. What's this vector going to be? We can see that we are going to have solutions, right? Because look at this row here. It tells us 0 times whatever equals 0. Okay, so that's one way of thinking about it. The other way of thinking about it is if the rank is less than n, then we know the rank plus the nullity has to equal n. Okay, and so if n is 3, for example, and the rank is less than 3, if the rank is 2, then the nullity has to be 1, right? So we have to have some nullity. We have to have vectors in the kernel, which means we have a kernel in the first place. Okay, that was a lot of information. Please ask questions, because this usually takes like 2 weeks to understand when you're taking the class, and I explained it in like 8 minutes. So please ask questions if these are not equivalent in your head. Because basically in problems, they're not just going to be like, oh, let's say matrix A has a determinant of 0. It could be like, let the rank of A be less than n, and you have to infer that that means that the determinant is equal to 0. Okay, so take a second. I'll leave the whatever like massacre I did on the board here, and see if you have any questions or anything that's confusing. And then this table here just summarizes it up and does it for the opposite case. So we said, right, it kind of goes in this order in my head. If the determinant is equal to 0, then A inverse does not exist, because clearly the determinant formula shows that. Then the reduced echelon form is not going to be the identity, because if the determinant of A equals 0, that means that somewhere in our matrix we have a row of zeros. And we reveal that when we row reduce it, right? And so that means that row reducing, we get a row of zeros, so not the identity. And then rank and nullity follow. And then these are basically the opposite, right? When the determinant is not equal to 0, the rank is exactly the number of columns, which means that we row reduce to the identity, right? We row reduce to something that looks like this, right? And in this case, the rank is exactly 3. The number of columns is 3. So the nullity is going to be 0, which means no kernel. Okay. Any questions? Because now we're going to divert to a completely different topic. Last chance. Okay. I would go back and like try and re-explain that whole thing to yourself uh, at the end because it's very important to understand these connections. Okay, now we're going to talk about vector spaces. This is probably where things are going to get new a little bit in terms of material. So what a vector space is, it's just a set of vectors. So it's a box of vectors. You think about it, you have a box, and inside it you have a bunch of vectors. Okay. Now these vectors satisfy two conditions. They're closed under addition and closed under scalar multiplication. So what does this thing closed mean? So let's say I have my box here. Okay, and instead of a box, I'm going to say I have a circle. This is my bag, okay? And I have some vectors here. Vector 1, vector 2, vector 3, vector 4. These are all just vectors in my vector space, okay? Closed under addition means that if I take two vectors in my space, so I select two random vectors in my space and add them, so I do v2 plus v3, and I get some result, okay? That result must also be contained in the vector space. If that result moves me out of the vector space, then we're not closed. So by closed, we mean that if we do addition, closed under addition means if we do addition on the vectors in our vector space, we better stay inside our vector space. Same thing with scalar multiplication. Is if I take a random vector v6, right, and multiply it by some constant c, my output star has to be in the vector space. Okay, so let's do an example. Let's see if, let's just logically think about, is R3 a vector space? So R3 is the set of all three-dimensional vectors. Okay, think about this for a second. You need to test one, is it closed under addition? And then is it closed under scalar multiplication? Okay, so closed under addition means if I take any two vectors from R3, let's just do an example. Let's take 2, 1, 3 plus 0, 0, 1. These are both vectors in R3. Is my result also in R3? Yeah, right? 2, 1, 4 is also in R3. So this guy is from R3, right? This guy is from R3. My result is also in R3. For this example, we're closed under addition. Now, the thing is, R3 needs to be closed under addition for all of the vectors. So obviously we could go through all the examples, but it's pretty clear that if I take two vectors in R3 and add them, I'm going to end up in R3 because I'm going to end up in three dimensions, right? Same thing with scalar multiplication. If I take any vector, 1, 2, 3, and multiply by any constant 5, I'm going to stay in R3. Okay, so we would say R3 is a vector space because it's closed under addition and closed under scalar multiplication. Just that's the intuition. Okay, let's see what other concepts we have here. So here we're explaining what closed under addition and closed under scalar multiplication means. Okay, another thing to keep in mind is that, right, if we have a vector space V, okay, and we have some vector in it, A, B, C. Let's imagine, okay? Because we know it's a vector space, so we know V is a vector space. So if V is a vector space, then we should be able to scalar multiply A, B, C to get negative A, negative B, negative C, right? That should be allowed because that's scalar multiplication. And then because addition is also allowed, we should be able to take this guy, add it to this guy. So we should be able to take A, B, C, add it to negative A, negative B, negative C, and get something that's still in the vector space. And this is always going to be 0, 0, 0, which must be in the vector space. It must belong to the vector space. So basically, if V is a vector space, it needs to have the 0, 0, 0 vector. Okay, so that's a key, like that's something you can use to immediately spot out if something is not a vector space. If it doesn't have the 0 vector, it's not a vector space. Okay, so we're going to see examples of not vector spaces later on. You might be thinking, what could not be a vector space? We'll see examples. But first, let's talk about subspaces. So these words are kind of confusing. There's a lot of words in this class, if you haven't realized. A subspace is just a more specific set of a bigger vector set. Okay, so like let's say my original vector space is R3. Okay, so R3 is going to be my original vector space. Okay, my subspace could be so a subspace could be all vectors in R3 where first element is 0. Okay, so all vectors of the form 0, A, B, right? All of these still belong to R3, They're just a more specific set of R3. Okay, does that make sense? We have something in the chat. Oh, okay, sign it. Okay. Yeah. All right. So a subspace is just a more specific. It's the same thing as the spaces we had before, but we just put another restriction on it. Okay. Now, to see if something is a subspace, same process. You test if it's closed under addition, closed under scalar multiplication, and if it has a zero vector. Okay. By the way, you don't have to test if it has a zero vector. That follows from the other two. So it's really just closed under addition and closed under scalar multiplication. Okay. So let's see. Is this thing that I mentioned? So I technically should not have called it a subspace. I should have called it a subset. Okay. Now let's test if it's actually a subspace. So subset, I've said, okay, this is my subset. Is this actually a vector space on its own? Is it a subspace on its own? Let's see. Is it closed under addition? If I have some 0 something something, okay, and I add it to another thing, 0 something something, what's my output going to be? 0 something something. But the idea is I don't care what this something something is. This is still in the subspace, right? Because the subspace says that the first element has to be 0. So here we belong to the subspace. Here we belong to the subspace. This sign means belong to, by the way. Here we also belong to the subspace because this first element is 0, right? So it looks like it's closed under addition. Let's see if it's closed under scalar multiplication. If I take some constant times 0ab, I end up with 0 something something. So as long as my first element is 0, I'm still in the subspace. So this looks like this subset is actually a subspace. Check. Okay, we'll do more examples. Here's an example right here. Notice how this subset S, okay, is defined as all 4D vectors where the first element is 4. Very random subspace, but it's still a subset. Sorry, not subspace. It's a very random subset. So we would say S is a subset of R4. Okay, if that makes sense, because R4 is all our 4-dimensional vectors, and S are the specific ones that follow this constraint where the first element is 4. Hopefully you guys can see that this is not a subspace. Why? Because look at this example right here. Here is a vector that belongs to S, right? Because its first element is 4. Here's a vector that belongs to S, but the output vector, when we add them, does not belong to S. Why? Because its first element is not 4. Okay, so that's how you can tell if something is not a subspace, is you just find one counterexample and you prove it like that. To show something is a subspace or a vector space, you have to do a general solution, which we'll see examples of. Okay, so let's go over some of the common vector spaces that we see in this course. R2, R3, Rn. So those are 2D, 3D, 4D, 5D, ND, whatever. Just a vector with that many entries. The set of all 2x2 matrices, that's a vector space, right? Because if I take a 2x2 matrix, add it to another 2x2 matrix, I have to stay, my answer is going to be a 2x2 matrix. There's no way around it. Same thing with multiplication. And the set of all polynomials, right? If I take a polynomial, add it to another polynomial, I'm going to get a polynomial. I'm never going to get something with like sine and cosine or whatever, right? That's not possible. It can't come out of nowhere. What's the difference between a subspace and a subset? So a subset, this guy is a subset, okay? Because it's you take a vector space and you put a restriction on it and you get a subset. So where specifically this guy is 4. It becomes a subspace only if it's also closed under addition and scalar multiplication. Okay, so basically a subspace is what we use just to call this thing, right? Okay, perfect, yeah. And then the subspace is when it also follows scalar addition and scalar multiplication. So this guy is a subset, but it's not a subspace. Okay. All right. Here's some practice problems. Look through. Okay, I'm going to show you problem 1. Problem 1 uses the fact that, okay, how do row operations affect the determinant? So let's just quickly go over the intuitions. Let's see. I have A, B, C here. So it looks like, okay, it looks like first D, E, F, and G, H, I have flipped. So that's going to be like some sort of multiplying by a negative, right? To flip those two. Then it looks like G has been, it looks like, okay, then it looks like we've taken 2 times A, right? Because that's how we get this guy. So times it by 2. And then it looks like we've also scaled GHI by 2, right? And this plus 3D is fine because, well, let's just go, I don't know. Let's see, what's the question? Oh, okay. So let's see. How can we do this? We can just like do it out. I don't know if this is like useful for you guys, but let's just do it out. So, the flipping operation just turns us into like A, B, C, and then G, H, I here, and then D, E, F, right? Then we multiply the A, B, C row by 2 to get 2A, 2B, 2C, G, H, I, G, H, I, and then D, E, F. And then to get 2A plus 3D, we just add 3 times this row to this row, which doesn't affect the determinant. And the last thing we do to times it by 2 is just times this row by 2 right here. So basically, we're going to take our original determinant A, multiply by -1, multiply by 2, multiply by 2, and then we get -12. Okay? Let's skip over problem 2 because that should be fairly straightforward. You guys say you know how to find determinants. Let's do 3. First, I want to try 3B because that one's a little bit more straightforward. Okay, so can you guys see? A little bit annoying. Take 2 minutes and think about. Okay, can you guys see the problem? Consider the vector space R3. Let's do 3B first, so ignore this guy for now. The set of vectors, I'll just write it up here. The set of vectors V1, V2, V3, such that V1 minus V2 equals 0. So think about whether this could be a subspace or not of R3. Then we'll go over how you can generalize it. Okay, let's not like spend too much time. So let's realize that okay, if V1 minus V2 equals 0, basically we're saying that V1 has to equal V2. So it's a good idea to in your head get a picture of what the subspace looks like, right? We're talking about okay, now that we have this, I'm gonna just go down to here so I can write it here. Okay, so let me clear and let me zoom in 1 sec. Okay, so we know V1 minus V2 equals 0. So this pretty much implies that V1 has to equal V2. So pretty much we're saying, okay, our original vector space is R3, but we don't care about that because we're looking at a specific case where our vectors are of the form V1, let's maybe call it, I don't know, A, B, right? Where the first 2 elements are equivalent. So let's do an example. What's an example vector in there? 1, 1, 2, right? This belongs to our subspace, right? Let's do another one, add it to another one, 2, 2, 3. This also belongs to our subspace. Okay, and then I add these vectors. 1 plus 2 is 3, 1 plus 2 is 3, 2 plus 3 is 5. Okay, this also belongs to the subspace, right? Because these 2 first elements are the same. So intuitively, it looks like it's going to be a good subspace, but let's prove it, right? So all we do to show, like, in general, is we just do it for a general case. So we say, okay, let, right, B be a vector in S. So S is our subspace here. Okay, so let AAB be a vector in S. We want to show that, okay, actually we need to take 2 vectors in S because we have to add. So let AAB be a vector in S. Let's do let AAB and I don't know, CCD be vectors in S. Okay, we'll show that we're closed under addition. How do we do that? We take our one vector from S, we add it to another vector from S, and we can see that we're going to get A plus C, and B plus D, right? Which we can see is also an S, right? And how do we know that? It's because these 2 elements are always going to be equivalent. They're equal, right? Let's check that it's closed under scalar multiplication. We choose a constant. So we can choose any one of these vectors. Now let's choose a constant, I don't know, W times AAB equals WA, WB, also in S. Okay? So this is a vector space. Okay? All right. Now, I think we'll take a break after this next problem. So let's do part A now, which is a little bit trickier, but same idea. Try part A, 3A on your own and see if there's a vector space or not. So we have V1, V2, V3, such that the first element times the third element plus the first element times the second element equals 0. So for this one, it's a little bit harder to like, on the previous one, we had v1 minus v2 equals 0. So we just said, okay, v1 equals v2. Here, it's a little bit harder to do that. So the approach that we'll take is we'll do this. We'll say, okay, let's do a1, a2, a3, and b1, b2, b3, b in S. Okay, so these are our test vectors in our subspaces. And because they're in S, we know, like behind the scenes, that A1, right, A1, A3 plus A1, A2 has to equal 0, and B1, B3 plus B1, B2 has to equal 0. We know this, right? This is a given because these vectors are in S, and any vector in S has to satisfy this property. Okay. Now let's construct the sum of them. So let's take A1, A2, A3 plus B1, B2, B3. So we're going to check for closure under addition first. We get A1, B1, A1 plus B1, A2 plus B2, and A3 plus B3. Now the question is this in S? Yes or no? I mean, we can't tell by just looking at it. So let's test, right? Any vector in S needs to have this property. So let's check if v1 times v3 plus v1 times v2 has to equal 0. So let's check if A1 plus b1 times A3 plus b3 plus A1 plus b1 times A2 plus b2 equals 0. Okay, and I think I've done this problem before. You do the algebra out, okay, and let's not waste time doing that. But you end up like, okay, maybe we just do it. A1, A3 plus A1, B3 plus A3, B1 plus B1, B3 plus A1, A2 plus A1, B2 plus A2, B1 plus B1, B2 equals 0. And as you can see, we have B1, B3 plus B1, B2. So that's B1, B3 plus B1, B2. Those are going to go away and turn into zeros. So get those out, right? And then similarly, A1, A3, A1, A2 are going to be 0. So A1, A3, A1, A2 are going to be 0. But we're still left with this equation that says A1, B3 plus A3, B1 plus A1, B2 plus A2, B1 equals 0. And there's no guarantee that this is true. Like this will be very lucky if this happens, right? We have no fixing on A1 and B3 to make this happen, or A2 and B1, right? So this is not a vector space because there's no guarantee that this is going to be true. So basically going back, there's no guarantee that this guy is in S. So which means that you're taking two things in S, adding them. The result is not guaranteed to be in S. So this is not a subspace. Okay. Let's take a 10-minute. Actually, wait, let me just see the next chapter. I think, yeah, let's take a little break before the next chapter and come back at like 4:25-ish. If you have questions, drop them in the chat.
So we have everyone registered except for one or two people. So thank you for
Yeah,
everyone that registered. So the one or two people who haven't yet, please do.
yeah, you know who you are.
Thank you, Autumn. Great so far.
Yeah, if you have questions, just type them in the chat in the meanwhile. I'm gonna go get some water. Okay, we have a few questions. I think I'll just answer. I'll answer those now. Wait, let me see. On the credit exam, is there a specific way they want you to show it? The way I approached it was looking that at the restriction value, the V1 had to be 0 or V3 had to equal negative V2. Yeah, that's valid. That's valid. However you want to approach it, I think, yeah, your way makes sense. The main thing is that you have to make sure to generalize it. So don't like do specific examples. If you want to prove something is a subspace, you need to generalize it for all possible. If you want to prove something is not a subspace, you can just find like one counterexample. Or for example, to say, oh, the zero vector isn't in it, so it's not a subspace. The difference between free pivot variables and their connection to rank nullity again. Yeah, basically, um, your okay, so we know that the free variables plus the pivot variables has to equal the total number of variables. Okay. Then the number of free variables is the rank of your matrix. Oh, sorry, not the rank, is the nullity. It's actually sure, whatever. The number of pivot variables is the rank of your matrix. So because when you have a matrix, right, and you find the rank, you're not only actually finding the number of non-zero rows, but you're finding the number of pivot columns. So that's the equivalency when you're doing the rank. So that's also how it can be defined. So the rank of A is the same as the number of pivot variables. And then the nullity of A is going to be the same as the number of free variables. Because remember, the nullity is the number of vectors, as in the number of like free vectors in your kernel. So remember, when we solved before, in that big system, we had like our solution to AX equals 0 was X, so the kernel, right? Because it's solving this equation. The kernel was what, like some vector plus T times some vector plus S times some vector, right? And that told us that, okay, we have two free variables because we've got T and S in there. So the nullity, right, of A would equal 2, which is the same as the number of free variables. So this is the same as this is the same as this, and then the total variables is just the number of columns. So if A is an M by N matrix, then the total variables will be N because we'll have N variables. So the rank of A plus the nullity of A has to equal N, the number of columns of A. Always. Okay. All right, we'll be back in like 3 minutes. Okay, one more question, and then let's also start coming back. The rank is the number of non-zero rows after row origin. The pivot is the number. How these are related? That's there's like a theorem that says that the row rank is defined as there's technically two types of ranks. The row rank is the number of non-zero rows, and the column rank is the number of columns that have a leading one. There's like a proof that shows that those two theorems are equivalent. Like it's mainly something that you take for granted for now. It's kind of it's hard to show the intuition. That's why my explanation was very hand wavy in the first place. Um, but I don't really know the big intuition behind it. I feel like they may have done the proof in like 2400, but it's not important to know where it comes from as much. Okay. Hopefully everybody's like back. Everybody's back, ready to move on. Um, we're moving. Wait, what? Wait, why is it showing? Okay, let's move a bit faster. I'm gonna move a little faster so we can finish today. But if I'm like, just please message confusions in the chat. Okay. All right. So linear combinations. Okay. A big word to know is a linear combination of vectors. What that means is you have a set of vectors. When we take a linear combination of them, we just scale them and add them to each other. So, like for example, this vector right here is a linear combination of these vectors because we can make it by taking 1 times this guy and adding it to 2 times this guy. So that's it. So 1, 2, 4 is a linear combination of these two because it equals 1 times this plus 2 times this. Okay? Now, when you have a set of vectors, we can call them linearly independent or linearly dependent. Linearly independent means that, okay, linearly independent means that you go to each, so let's say we have a set of these vectors, right? This is our set of vectors right here. We go to each vector and we say, okay, can this vector be made as a linear combination of the other vectors? Can this vector be made as a linear combination of other vectors, et cetera, et cetera? Okay. In this case, these would not be linearly independent, right? Because we just showed that this vector right here can be 1 times this vector plus 2 times that vector. So this would not be a linearly independent set. This would be a linearly dependent set. Okay. How do we determine if vectors are linearly independent? Feel free to read this explanation. It's hopefully it's clear. But the idea is what we do is we just set up this equation right here. We say, okay, if we're looking to test for n vectors, so v1 through vn, okay, we set up the equation c1 v1 plus c2 v2 plus all the way cn vn equals 0. And we solve the system of equations for c1, c2 all the way through cn. Okay. If we're always going to get a solution because why? Because 0 for all the c's is always going to be a solution, right? 0 times this plus 0 times that is always going to be 0. If that's the only solution, then they're linearly independent. So it actually says it right here. If the only solution is the trivial one, the obvious one, then they're linearly independent, your vectors. But if you're able to find another solution for C1 through Cn, for example, like C1 equals 1, C2 equals 2, and C3 equals 4, then V1 through Vn are linearly dependent. So let's go through an example. Okay, so obviously two ways of determining. One way is you just inspect. You look at this set. Okay, so maybe we can even see that with this example. Yeah, if you go to the example, right, are the following linearly independent? Hopefully you do a little bit of guessing and checking, and you can see that, okay, if I take this guy and minus this guy, so 1 times this plus -1 times this, I get the third vector. So clearly they're not linearly independent. And this example is a little bit easier, but sometimes it's not going to be so obvious. So how do we prove it generally? Okay, what we do is we set up this equation. So we set up C1 times V1. So actually, I probably have it written down underneath. Yeah, right. We set up this equation. So here are our three vectors, right? 2, -4, 5, 3, 2, -4, -1, 6, 9. We say C1 times V1 plus C2 times V2 plus C3 times V2 equals 0, 0, 0. And we see if this has a solution that's not all zeros. So we hopefully at this point know how to solve this. We know how to solve this. We row reduce, blah, 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 blah. We can see that the row reduced echelon form turns into this. So one more time reviewing, right? That means that if we do, C1, C2, C3 equals 0, 0, 0, then we're saying at the bottom, we already have a free variable. So that's infinitely many solutions, right? So that's no good. I mean, that means that C1, C2, C3 have many solutions. It's not just 0, that's the only solution. So because we find solutions other than C1, C2, C3 equals 0, we know the vectors are linearly dependent, which is what we showed before. Cool? Okay, makes sense. Next, we talk about the span. So the span of a set of vectors is basically the reach. It's all the vectors you can make with those vectors. So you think of these vectors as building blocks. So let's say we have a set, a vector set or vector space. It's a vector space, right? This is R2, right? 1, 0, 0, 1. The question is, what is the span of S? So that's asking, how can, when I take linear combinations of these vectors, what vectors can I make? So with the vectors 1, 0 and 0, 1, you can take like 2 times this one plus 3 times that one and -1 times this one and -3 times that one. You should realize that you can make any vector in R2, right? If you want to make the vector AB, you just take A times the first vector plus B times the second vector. So thus we say the span of S is R2. Another way you'll hear span being used is you'll say this vector set spans R2, or these vectors span R2. So span is a little bit confusing. You just get used to it. Span is like a noun. So you can say like the span of this vector set is R2, but it can also be a verb. Like these vectors span R2. Just, yeah. This you'll get used to it. Okay. But for example, if like my vector set, if my vector space was like, if my vectors were 1, 0, and 0, 0, this does not span R2, right? Now the span of S, right, is going to be all the vectors. It's going to be a subset of R2, which is going to be of the form A, comma 0, right? Why? Because I can make any A I want. Because I have my 1 here, I can take A times this vector and make whatever A I want. But I can't make whatever I want in the bottom because I only have zeros and zeros here. So no matter what I take, linear combination of these, the bottom is always going to be 0. So here the span of S is going to be A0, which is a subset of R2. And hopefully these words should start making sense now. So that's where the subset word can help us come in. Also, this A0 is not a subspace, right? Because it's not going to be closed under addition. Anyways, okay. Now, last thing I should talk about is a basis, okay? So a basis is a set of vectors, okay, that we use to build an entire vector space. So let me just give you an example, right? A basis of R2, okay, should be vectors with which we can reach the entire R2. So we just found one above, right? A basis B could be 1, 0, 0, 1. Right? Because with these two vectors, we can span the entirety of R2. We can get any vector in R2 by combining these vectors. Now, what's also special about a basis? So if you check this out, a basis of a vector space is a set of vectors that span the space. Great, excellent. But there's another characteristic, which is that they're linearly independent, i.e. there's no redundancies. So just like here, I actually write this example right here. Just like this set spans R2 as we saw, this set also spans R2, correct? It just has an extra vector in it. But the question is like, why is that extra vector there? We don't need this 2, 2. It's redundant, right? Because we already have these two that are spanning. 2, 2 is actually itself a linear combination of these two vectors. So it's linearly dependent, right? So that's why this set would not be a basis. To turn it into a basis, we have to get rid of the linearly dependent vector. Okay, so a basis of a vector space, for example, this guy, it can span any vector in the space, so you can take combinations and make any vector in the space. It's also linearly independent, which means there's no redundancy. So you can also think about it as minimally spanning. It's the minimum set of vectors you need to span the vector space. There's no extras. Okay, here are some examples. R2. Notice how I say here how we say these are standard bases. Okay, so the usual basis we use for R2 is 1, 0, 0, 1. However, if someone were to come up to you and say, oh, in my world, I like to use this basis, 2, 0, and 0, 2. That's still a basis. It's a very valid basis, right? The vectors are linearly independent. You can't form one using the other, and they span the entirety of R2. It's just going to be different coordinates, and we're going to talk about that in the next chapter, okay? But the standard basis, we're used to seeing this basis right here. Same thing for R3, okay? P3, this should be a term you should get used to seeing now. P3 means the set of all polynomials up to degree 3. So degree is the highest power in the polynomial. So P3 is basically any polynomial of the form 1 or A plus bx plus cx squared plus dx cubed. Okay, and so obviously a basis is going to be all of those basis polynomials because you can just add those up and scale them to get whatever polynomial you want, right? If I want to get 3x squared plus 5x, I'm going to take 0 of this guy, right? 0 of this guy, 5 of this guy, 3 of this guy, and 0 of this guy, right? Same thing, R2 by 2 is the space of all the 2 by 2 matrices. It needs to have 4 basis vectors or basis matrices because we have 4 entries, right? And then underneath we can see we're saying these are not the only basis, right? And another basis is this one or a different one, and we're going to talk about that later, switching between different bases, okay? Another key word is the dimension of a vector space. The dimension of a vector space is the number of vectors in the basis. So R2, we would naturally say it's two-dimensional, and that makes sense, right? Because there's 2 vectors in the basis. Here we say R3 is 3-dimensional. P3 is actually 4-dimensional because we need 4 vector space, 4 basis elements to span the vector space, right? R2 by 2 is also 4-dimensional. And that should make sense, right? The set of all 2 by 2 matrices should be 4-dimensional because there's 4 elements. Okay. Okay. Right. So any basis of R3 is going to have 3 vectors. It doesn't matter what kind of basis. There's an infinite amount of them, but they're all going to have 3 vectors. Okay, this is probably one of the most confusing parts, especially of this like first section. So let's spend some time on it. How do we change between bases? Okay, so the first thing is, if I tell you before you even came to this class, right? Or this session, or if I told you, okay, give me the vector 2, 3. Okay, you would in your head, if you had a coordinate plane, you would go on here and you would say, oh, 2, 3, duh, 2, 3, right? You're naturally in your head breaking this up as 2 times 1, 0 plus 3 times 0, 1. Why? Because these are the standard basis vectors that we use in our lives, and this is the standard basis. So that's why you're going to say that, okay, when I say 2, 3, I'm talking about this. That was not straight. This vector right here, okay? However, again, however, we could also be on an alien world where, let's say, their basis is given by this. So our basis is this. Their basis is 2003. So in that case, right? So the representation of 2, 3 as a point in our basis is 2, 3. Does that make sense? Right? Because we basically say 2, 3 in the standard basis. Okay, so basically 2, 3 in the standard basis will get us to this point right here. Okay, how do we get to this point in the new basis? Well, are we going to take 2 of this guy and 3 of this guy? No, we're going to take 1 of this guy and 1 of this guy and add them together. So what we're really going to say, we're going to say 1, 1 in the new basis is going to also correspond to the same point. Okay, so let's go over it again, right? 2, 3 in the standard basis means you take this number times the first basis vector plus this number times the second basis vector, and you get 2, 3. Excellent, because that's what we want to get, right? Now 1, 1 in our new basis is going to be this number 1 times this basis vector 2, 0 plus this number times this basis vector, which if you notice, it's going to be the same exact thing. So as you can see, there's multiple ways of getting to the same point, depending on your basis. Okay? So the key idea is down here, which is that this vector 2, 3, like this actual vector, has different representations depending on what basis we choose. Okay, so we're going to figure out how can we learn to switch between different bases. So let's scroll down. Okay, here's an example where we're showing that, look, if you have this notation, a vector ABC under basis B, means you do A times the first basis vector plus B times the second basis vector plus C times the third basis vector. Okay, hopefully that's clear. So here we say if only we had a matrix that would make blah, 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 and we do. We're going to figure out how to find this matrix. So we want a matrix that goes, the way we call it the change of basis matrix. Change of basis matrix. This is going to be a matrix that we call P from, let's do B to S first. Okay, we want a matrix that goes from B to S. So that means if I have a vector and I have its representation in B, I want to be able to multiply it by this matrix and get out the vector's representation in S. Okay, make sure that ordering makes sense. We're starting with a vector in B, we're multiplying by change of basis matrix from B to S, and we're ending in a matrix with a vector in S. Okay? How do we find this matrix? It's gonna be it's gonna actually look like a matrix. How do we find it? Here's like the key line. Okay, and this is usually the most confusing part. To determine P from B to S, we must represent the basis vectors in B in terms of the basis vectors of S. Okay, the way I remember this is like, let's say I'm going to Mexico for vacation. Okay, and in Mexico they use pesos, right? So the two different currencies here, my currency is US dollars, and in Mexico they use pesos. If I'm going to Mexico, I'm moving from my basis in the United States to Mexico's basis, right? And I want to be able to spend money. I need to represent my US dollars in terms of Mexican pesos. So I need to represent the basis vectors in B, my original space, in terms of the basis vectors in the new space. So I can see like, okay, what's going on here, right? Not the other way around. That wouldn't make sense, right? I'm coming from B, so I know my basis vectors in B. Let me represent them in terms of S, okay? That probably made no sense, but let's see an example. Okay, so here's how we're gonna find B to S. Okay, so first we take the basis vector. So let's rewrite our bases up here. So we know S is 1 0 0 1, right? And then B is right here, but I'll write it again. B is 2 0 0 3. Okay, so we're going from B to S, correct? So we want to represent the basis vectors of B in terms of as linear combinations of the basis vectors of S. So we start with the first basis vector of B. So first vector in B. What is that? 2, 0. We need to represent it as a linear combination. So some number times the first vector in S plus another number times the second vector in S. This is a linear combination of S. That makes sense? We're writing each vector in B as a linear combination of S. So here's the first vector of B. So as you can see, we did it here. We go down here and we solve. We can solve and say, okay, obviously A has to equal 2 and B has to equal 0. Okay? And you keep that in mind, okay? And in our P, let's start to form our matrix, right? That is going to go in the first column. That A, B is going to go A on top, and then B is in the first column. That makes the first column. Okay, we did it for one vector in B. Now we have to do it for the second vector in B. So what's the second vector in B? 0, 3, right? So you say, okay, 0, 3. How do I represent this as some number times the basis vectors of S plus another number times the other basis vector of S, right? And here you can see, okay, C is going to equal 0, D is going to equal 3. And so you're going to put 0 and 3. And this is the change of basis matrix. Okay, so what this matrix does is it allows us to take a vector in B, a vector representation in B, and find its equivalent in S, right? And so remember, for the actual vector 2, 3, right, our representation in B, so 2, 3, it was equal to 1, 1 in B, and it was equal to 2, 3 in S, right? So hopefully, if we do this matrix multiplication, if we take 1, 1 in B, right? So if we take 1, 1 in B and multiply it by P, B to S, we should get out 2, 3. That's kind of the idea. And that matrix multiplication does work if you test it. Okay? With three-dimensional vectors, it's the same. With three by three matrices, it's the same. It just gets a little bit more algebra heavy because you have to solve for like A, B, C, and those are all going to go in one column. And then D, E, F is going to go in the next column, etc. Okay. Now, how do we find blah, blah, this works, this works? Okay, one important thing to note is that if we wanted to do the other way around, so if we wanted to find, we found P from B to S, if we want to find P from S to B, right, there's two ways. There's a nice formula, and this also intuitively makes sense, that if you have this matrix here from B to S, and you take its inverse, that's going to give you the matrix from S to B. So you invert it and you'll get the other direction. The other thing you could do is just like do the whole process out again. So instead of representing each basis vector of B in terms of S, you represent each basis vector of S in terms of B. Okay? All right. Here's another example down here. We honestly just did an example. So let's skip this and maybe go to the practice problems. Let's see. Yeah, okay, let's do these practice problems. Since change of basis and is fresh in our mind, let's do problem 2 first. Okay, try this one out. Actually, let's just do it together. Why are you spending time? Okay, so determine V, the representation of V in B. So we know V is 1, 0, so we're looking for 1, 0 in B. Remember, what does that mean? It means you take 1 times the first basis vector of B plus 0 times the second basis vector of B. And that gives us 1, 2. Okay, now let's do 1, 0 representation in C. Same idea, right? So obviously this is VB and this is VC, right? 1, 0 in C is going to be 1 times the first basis vector of C plus 0 times the second vector in C, which is going to be 7, 3. So as you can see, this same vector represented in B and represented in C takes you to completely different places. That's what's important to know. Okay, find P, B to C, and find P, C to B. Let's go and set up the problem. So let's find P from B to C. So again, we represent basis vectors of B in terms of basis vectors of C. Let's go to the first basis vector of B. What's that going to be? 1, 2. And we represent that as linear combinations of like A times 7, 3 plus B times 4, 2. And then you solve for A and B and you stack those into a column like that. Then you're going to do it for the second basis vector of B, right? That's going to be 3, 4. Okay, this is going to equal, okay, C times 7, 3 plus D times 4, 2. And you're going to solve for C equals what, D equals what, and put those like that, and that's going to be your answer. Then to find the other one, I wouldn't go through the process again. I would just find the inverse of that matrix, and then you get the other direction. Okay, so hopefully we'll post solutions very soon so you can verify your answers. But yeah. Okay, and also one thing is, in here we don't have a ton of practice problems. Hopefully in the next few weeks, like leading up to the placement exam, we're just gonna make a central doc with a bunch of more updated practice problems and like their solutions. So you should keep checking for that. Okay, let's do A. Okay, try this one. This one's kind of a logic one. Find a basis for the subspace of 2 by 2 matrices. So this is where we're using subspace again, right? Because 2 by 2 matrices is the entire space. We don't care about that. We care about the subspace that has this specific property, that A plus A transpose equals 0, i.e. A equals negative A transpose. This should come up again, as we see. This means that A is skew-symmetric matrices. So our subspace is the space of skew-symmetric matrices. Can you find a basis for it? So can you find, remember that for all 2 by 2 matrices, right? What was our basis? Well, we needed a matrix to make this guy, right? We need this guy, and this guy. Right, that was our basis for all 2 by 2 matrices. But now we're talking about a very specific type of matrix, which are skew-symmetric matrices. We already know from a previous problem that the diagonal of skew-symmetric matrices has to be 0. That's good. That means we don't really need any vectors like to represent that, right? The idea here, oh, I have a little bit of typo. This should be 0. Yeah. The idea here is that we need a 1 here and zeros everywhere else so we can customize this top left corner. And this one lets us customize the top right corner. Here we don't have to customize anything, so those are fine, right? And we should realize that the skew-symmetric matrices, when it's 2 by 2, is going to take this form, where A is there and negative A is at the bottom, right? Because then when you transpose this, right, it's going to turn into, when you take the transpose, it's going to turn into 0A, negative A, 0, which you can see they're negatives of each other, okay? So basically what I figured out is that all skew-symmetric matrices look like this, something of the form this, okay? And then you say, okay, how many variables do I have here? You have 1A. So you should only need one basis to describe this. What would that be? It would be this basis, right? 0, 1, negative 1, 0. Because I can multiply this by any scalar multiple and get a matrix of this form. Okay, so here's a basis, here's the answer, here's your basis for the subspace. What's the dimension of this subspace? It's going to equal 1. So we'd say that the dimension of the subspace of skew-symmetric matrices is 1. It's a one-dimensional subspace. Versus the original matrix space is 4-dimensional. That's why there's a subspace. It's less dimensions. Okay, any questions about those problems? We're doing it okay on time. Uh, this one is also a good one. Um, let's not go over exactly the math, but let's go over how we would do it. Um, given the set, so here's a set of, oh, do you have a question? Why can't 1, 1, 1, 1, and 2, 2 in a skew symmetric matrix be a number? Wait, sorry, one more time. Let me go up to the other problem. Why can't, if you want to just unmute and ask, it might be clear if you can unmute. Otherwise, you can just type in the chat again.
Yeah, I mean, like, could we have a matrix that's like 3 A, negative 3?
3a, -a, -3. Think about this, right? This is what we talked about in the first problem with like the trace of a skew symmetric matrix. If you have numbers along the diagonal, right, and you take the transpose, those numbers always stay the same. Because if you notice 3a, you write it as 3a, and then -a, -3, you write it as -a, -3. Notice how this is a, right? This is a transpose. They're never going to be negatives of each other
Oh, the
because
negative 3 isn't negative to the
negative
negative 3.
right?
Okay,
So the
I see.
only way
Thank
it's going to
you.
be negatives is if you have zeros along the diagonal. Yeah, yeah, good
Thank
question.
you.
Yeah, yeah. So that's why. Otherwise, it would be a little bit more tricky. You'd have to have more like the basis vectors. But the general logic is you say, okay, I'm looking for I'm looking for skew symmetric matrices, right? What does a skew symmetric matrix look like? As soon as you figure out that it takes the form 0, 0, a, -a, then you know, okay, I've got one variable here, right? Um, that's why I need a one-dimensional subspace. I need one basis, right? That same logic applies. If you're looking for the basis of all matrices, you say, okay, my matrix can take the form A, B, C, D. Each one of these could be different variables. That's why we're four-dimensional, right? That's why we need four basis vectors. Okay, good question. All right, this one. Does S span the space of 2 by 2 upward triangular matrices? So let's think about what that looks like. 2 by 2 upward triangular matrices are going to look like A, B, C, 0, right? A diagonal, everything above the diagonal is non-zero or could be non-zero. Everything below must be 0. Okay, so we've got two questions here. Is S linearly independent? Does S span the space? So to find linearly independence, right? You can basically turn these matrices into vectors. Let's tackle this first, right? You turn this guy into vectors. So you turn 3, -1, 0, 4, however you want it, or -2, 1, 0, 3, right? You just unfold all these matrices into vectors, and then you do your C1 V1 plus C2 V2 plus C3 V3, and then you're gonna have plus C4 V4 because you've got four vectors equals 0. One sec, I need to move my screen a little bit. Okay, equals 0. And then you solve and you see what you get for C1 through C4, and then that helps you determine it. Okay. In terms of spanning the space of 2 by 2 upward triangular matrices, what you have to realize is that, okay, basically this bottom 0 is kind of irrelevant for the whole problem, right? This, you can represent a 2 by 2 upward triangular matrix as just A, B, C, where A is the number here, B is the number here, and C is the number here. So pretty much this is the same question as asking, does, okay, 3, -1, 4, -2, 1, -3, -1, -2, 1, and 6, 2, 3, does this span R3, right? Does this span any three-dimensional vector? Because if we can, with these three, right, with these three, with these three, if we can form any three-dimensional vector, then we can form anything we want here, and then we can form any upper triangular matrix, right? So that's what you'll be asking here. The way you can figure this out, right, is think about, okay, you'll figure out if these are linearly independent. I think the answer to this one is that they're not linearly independent. One of them is going to be dependent on the others. So let's say this one is dependent, you take it out. Okay. Even though they're not linearly independent, these three, right, you check on these now. Are these linearly independent? If these are, then they will span R3, right? Because we have three linearly independent vectors. They have to span R3 as long as they're three-dimensional. Because remember, the dimension of R3 is 3, right? Which means as long as we have three vectors in our basis, it's a valid basis, and they're linearly independent. Okay, is the identity in the span of S? So that's basically asking, okay, with my vectors here, right? Instead of setting C1 plus equal to 0, you're going to set it equal to 1, 0, 0, 1, right? You're going to see if with my vectors here, can I add them up somehow and get to the identity? So you're going to solve that system. Okay. Let me clear this. Same thing here. You're going to see, okay, does this system have a solution where the right-hand vector, this vector right here, would be, I don't know if you can see my like thing waving. Yeah, but this vector here would be whatever, 1, 0, 1, 0, 0. Okay. I don't want to spend time doing the math and that. We can come back to it if we need to. This one, determine if the sets of vectors are linearly independent. Same idea, right? All you're going to do is like for 4a, right? You're going to say, okay, C1 times -3 to -3 plus, I won't do it all out, C2 times the other one plus 3 times the other one equals 0. And then you see if this has any solutions other than C1 equals C2 equals C3 equals 0. And that's why it's very important to know how to row reduce, to know how to quickly and efficiently solve these systems, because they're going to pop up everywhere. Okay. Any questions up until this point? I think next we talk about, yeah, okay. Any questions? Okay. Row space, column space, and null space. This is like kind of what we've been building up to. The row space of a matrix is the span of its rows. It basically says, okay, here's my matrix A, right? Here are its rows. Can I highlight it? Here are its rows. What can we make with these rows, right? So if I had a matrix like 1, 0, 0, 1, right? What are the rows of A? If I write them as like vertical, they're going to be 1, 0, and 0, 1. So we would say the row space of A, right, is R2, because these rows can span R2. They can make anything in R2. Okay, so how do we find a basis for the row space? So how do we find, like, if you think about this vector, right, the rows themselves are a basis for the row space, right? 1, 0 and 0, 1 are a basis for the row space. But what if I have a matrix that looks like this? This is 1, 0, 0, 1, 0, 2. If you notice, right, this third row here is kind of redundant, right? The row space is still R2, right? Because these two vectors make R2 and this guy is just like kind of tagging along. It's an extra guy. So a basis for the row space would still be, like, a basis for the row space would be 1, 0, 0, 1. So basically we would remove that redundancy. So how do we remove that redundancy? We row reduce. Okay, so if we were to take this matrix and row reduce it, what would we get? 1, 0, 0, 1, and then we do 2 times this guy minus 2 times this guy and get 0, 0 here, right? And then what we do, so step 1 is you row reduce the matrix. Step 2 is you take the non-zero rows of the reduced matrix. So to get our basis, we take this guy as one basis vector, and this guy as the other basis vector. This guy, bye-bye. So that's kind of the power of row reduction. It reveals to you which one of your rows are not giving any additional information, right? These two help us get to R2. This guy doesn't provide any additional information. Okay, you also could have obviously row reduced and turned this guy into 0, and then these would be your basis vectors, and that's totally fine too. Whichever one makes more sense. Okay, that's how you find the row space. If you, as you can see an example here, if you have this matrix, right, you can't just take the rows because they might be linearly dependent. So what we do is we row reduce, and as you can see, we row reduce, and this bottom row turns into all zeros. That means that we're only going to take these top rows as our basis vectors. Okay, similarly for the column space, oh, a little bit extra. The rank of a matrix is the number of non-zero rows. We already talked about that. And so the rank is also the dimension of the row space. So those are equivalent, right? Because the number of non-zero rows you have left, that's the rank. That's also as the number of vectors that are going to go in your row space basis. So that's the dimension. Okay, column space, similar idea. It's just the span of the columns of your vector. What you do, however, is you row reduce the matrix. You find the pivot columns. So you don't look for non-zero, you just look for pivot columns. And then, so let's say we have our matrix here. We row reduce. We take these pivot columns. So we know we're going to be dealing with the, let's see, we know we're going to be dealing with the first column and the second column, but we don't take those columns. We go back to the original matrix and find their locations, and we take the original columns that are in those places. That makes sense? the reason why we do that, so like here, we're not going to take 1, 0, 0, and 0, 1, 0. We're going to go back and we're going to say, okay, which columns are in the first and second place? These two. So we take those. The reason is because the reason we didn't have to do that with the row space is because we're row reducing. So that preserves relationships among rows. That can kind of screw up things along the columns. And so that's why we have to go back and just take them originally. Okay. It's not that deep to think about. You just know the process. Okay. Again, the rank of a matrix is also equal to the number of pivot columns. So this went back to the question of like the rank is very powerful because the rank is the number of non-zero rows. It's also equal to the number of pivot columns. So the rank is the dimension of the row space. It's also the dimension of the column space. Okay, both. Lastly, the null space. So we did row space, column space. Last one is null space, which you've talked about, right? It's the kernel. It's the same idea. So the way you find your null space is you row reduce, and then you solve ax equals 0. The same way we've been finding the kernel the whole time. Okay, so here you row reduce, and you solve your null space equation, and then you get, right? Then you'll get some solution like x1 equals 0, in this case, x2 equals 0, and x3 equals t. x3 equals t. That means your solutions are going to be of the form 0, 0, t, right? Or another way we could think about this is 0, 0, 1 times t, however you want to think about it. But you have one vector in your kernel. So because you have one vector, the nullity would be 1. The dimension of the null space is 1. So now you can think of the null space as an actual vector space. This is a vector space. How many vectors does it have in it? Right? 0, 0, 1 is its vector, right? Technically, this t doesn't need to be there anymore because when we say a vector space, we can take multiples of this as many as we want. We can take linear combinations as much as we want. Okay. Okay, again, back to the rank nullity theorem. Again, hopefully now it should make a bit more sense, right? The in our example above here, the rank, so we can do either way, right? We can do column space, right? The column rank is 2 because we have two two pivot columns. So 2 is the rank, or we can get the rank by going up here and saying, okay, we have 2 rows that are non-zero, so 2 is the rank still. So 2 is our rank, either way, and the nullity, the null space, has dimension 1. So the nullity is 1. So 2 plus 1 equals 3, the total number of columns. So always a good way of checking your work. Okay. This one, let's do this example. I think, yeah, I have it row reduced here, so let's not waste time row reducing. But if we go to reduced row echelon form, we get that the reduced row echelon form looks like 1, 0, 0, 1/3, 1/3, 0, 1, 0, 4/3, 7/3, and then 0, 0, 1, 1/3, negative 2/3. Okay, so let's find the row space. Let's do row space first, right? Row space, we say, okay, where are my non-zero rows? Well, all of them, right? So basis for the row space is going to be, you just take all your rows. 1, 0, 0, 1/3, 1/3, 0, 1, 0, 4/3, 7/3, and then 0, 0, 1, 1/3, negative 2/3. Okay, done. Column space, all right, we go for all the pivots. We find all the pivots, so column space, right? Pivot here, pivot here, pivot here. These two columns are bye-bye, no need. But remember, we don't take the actual columns here. We take them from the original one. So we take this one, and this one. The column space is going to be spanned by 3, 1, 2, 2, 3, 4, and 1, 2, 3. Okay, and then the null space, right? That's just solving this guy times, remember we have 6 variables. So 5 variables, x1, x2, x3, x4, x5 equals 0. Okay, so let's do that. Let's just do that to see. Okay, x4 and x5 are going to be our free variables because we know x1 through x3 are pivots. So let's write it out. We get, let's just do this example. I know this might be a little bit repetitive, but it's really important to be able to consistently solve this. So let's do the multiplication now. 1x1 plus 0x2 plus 0x3 plus 1/3 x4 plus 1/3 x5 equals 0, right? The next row tells me x2 plus 4/3 x4, sorry, 4/3 x4 plus 7/3 x5 equals 0. Okay, What's next? And the third row tells me what? X3 plus 1/3 x4 minus 2/3 x5 equals 0. So then again, we rewrite all the pivot variables in terms of the free variables. So you say, okay, x1 equals negative 1/3 x4 minus 1/3 x5. X2 equals negative 4/3 x4 minus 7/3 x5. And x3 equals negative 1/3 x4 plus 2/3 x5. Right? And then we say, okay, x4 and x5, let's call x4s and x5 t. So we're pretty much going to say, okay, our null space is going to be two-dimensional, right? Let's write out the overall thing. So we're going to get our solution is x1 is going to be, it's going to look like this, right? Negative 1/3, negative 4/3, and then negative 1/3. So write it like this, times s plus negative 1/3, 2/3. I think it's a positive 2/3, right? Oh, that's 7. Never mind. That's a 7. And that should be negative as well. Negative 7/3, and then 2/3 here, positive, times t. Something like this, right? So this would be your solution for x1 through x5. And then to put it in the null space, right? Finally, we're going to say, okay, we have two free variables, so the null space is going to be dimension 2, and it's going to be negative 1/3, negative 4/3, negative 1/3, and then negative 1/3, negative 7/3, 2/3. Okay, so as you can see, ready? This is the nice part. The rank of M is the dimension of the row space, which is also the dimension of the column space, which you notice are both 3. Good. The nullity of M is the dimension of the null space, which if you notice is 2, and 3 plus 2 equals 5, which is the number of columns in M. So we did it right. Good hint that you did it right. Okay. This is a classic problem. I would be very surprised if something of this form doesn't come up. So I would do it. Same idea for this one. More practice finding row space, null space, column space, more interesting matrices. So do these. We won't do them now. Let's see what's next. Okay, this one is also like, okay, this one's a sort of thought process problem. Let's come back to this one if we have time. Do we have questions? I think next. Okay, do we have any questions so far? Sorry, yeah, this is a lot of information in one at once, but hopefully like some dots are connecting. Okay. And now we move on to linear transformations. So a linear transformation is something that takes in a vector and outputs another vector. So linear transformation could be a machine that doubles all the elements of your vector. So we'll take in the vector 1, 1 and output the vector 2, 2. Okay, or whatever. Okay. Like here's an example, right? T would be your transformation, right? It's like a function kind of. It takes in a vector and outputs another vector. We call linear functions linear because taking the transformation, we call linear transformations linear because doing the transformation on the sum of two vectors. So basically you could add the two vectors and do the transformation on them, or you could do the transformation on the first, the transformation on the second, and then add them together. Those will be the same. Those will give you the same value, the same output. Same thing. You could scalar multiply the vector and then do the transformation, or you could do the transformation and then scalar multiply. It doesn't matter. You're going to get the same output. You're going to get the same output. So that's what linear means. Less important for this class, but it's important to at least get like why we're calling them linear transformations. Okay. The key idea is that linear transformations are matrices. Matrices are a representation of linear transformations. Why? Let's think about this matrix right here. It's a linear transformation. And what does it do? It multiplies by a vector and gives you a new vector. So this A is like our machine. You put in an input vector, you do the multiplication out, right? So this guy times this guy, 3 times 2 plus 1 times 1 is 7, and then 4, right? And you get a new output vector. So A, we would say A goes from R2 to R2. Why? Because it takes a two-dimensional vector, multiplies it, and ends up with a two-dimensional vector as well. So going from R2 to R2. Okay. In general, if a transformation is given by T from R, if a transformation is going from Rn to Rm, then the matrix must be an m by n matrix. And this should make sense because if your matrix is m by n and you're going from Rn to Rm, then your input is going to be like n by 1, and your output is going to be flattened m by your output is going to be m by 1. Yeah, your output's not going to be flat. It's going to be like this, right? So like for example, if we have a if I have a 3 by 4 matrix, right? Right? What's that going to look like? You're going to have 3 here and 4 here. So it's going to take in a 4 by 1, right? It's going to take in a 4 by 1 matrix, right? And it's going to output a 3 by 1 vector. It's taking a 4 by 1 vector and output a 3 by 1 vector. So it's going to go from R4 to R3. Okay, and you can see that here, right? It takes in an n-dimensional vector, multiplies it, and you end up with an m-dimensional vector, okay? That's a good trick to know. Here's how we find the matrix of a transformation. So usually the problems are going to be like this. Find the matrix of the transformation for this transformation from P3 to P2. So it takes us from polynomials of degree 3 to polynomials of degree 2, such that P of P, so it takes in a polynomial, and it outputs 2 times P prime minus 3 times P double prime plus P. Okay, very random transformation, but we can represent this whole thing as a matrix, okay? Now, this may not be so clear, right? Here it was clear how we can represent it as a matrix because, duh, we have vectors and we're multiplying by matrices to get new vectors. Here, where are vectors, right? There's no clear vectors. We're dealing with polynomials. So what we need to learn is how can we choose a basis for the input space? So how do we choose a basis for P3 so that we can represent things as vectors? Well, let's think, right? What is P3? It's vectors of the it's polynomials of the form a plus bx plus cx squared plus dx cubed, right? What's a good basis for P3? Right? Let's say a basis is a good basis for P3 is 1x, x squared, and x cubed. Okay, those are still not in vector form. What we do is we say the basis is now 1, 0, 0, 0, 0, 1, 0, 0. Right? Now think about what these basis vectors represent. 0, 0, 0, 1. Okay? 1, 0, 0, 0 means take one of this guy. So this translates to the polynomial 1. What does 0, 1, 0, 0 translate to? X. This will translate to x squared, and this will translate to x cubed. So now we can take any combination of these vectors we want, and we can get any polynomial. Right? If I take 3 of this, 5 of this, and 7 of this, I've made 3 plus 5x squared plus 7x cubed. Okay, so now we have a basis for our input space. Then we're going to apply the transformation to each one of these basis vectors. Okay, so we're going to do, if the transformation is t, we're going to do t of this guy. We're going to do t of this guy, t of this guy, and we're going to see what comes out. Then we stack those output vectors as columns, and that's how we form MT. So let's walk through this example real quick. Okay, everybody understand what t is doing? It's taking in some polynomial, right? And it's outputting 2 times the derivative of that polynomial minus 3 times the second derivative of that polynomial plus the actual polynomial, okay? And that's why it goes from P3 to P2, right? Because even if we have a P3, if we have an x cubed term, as soon as we take this derivative, that's automatically going to get bumped down to a x squared term. So we're going to end up with only degree 2 polynomials. Okay, so here's the steps. Let's choose a basis for the input and output spaces. So we did this. We're choosing P3, our basis is going to be 1x, x squared, and x cubed. And B2 is going to be 1x and x squared. Okay, and here, right, we're going to represent our polynomials, we talked about this too, in terms of vectors, right? So this polynomial, we're going to write it as 1, 2, 3, 5. And that shows the power of vectors, right? This vector is just saying 1 times the first thing in the basis, plus 2 times the second thing in the basis, plus 3 times that, and then we get our polynomial out that we wanted in the first place, okay? So let's apply the transformation to each basis vector in P3. So we're going to do t of 1, we're going to do t of x squared, and t of x cubed. Let's do t of 1 first. Remember, the formula is it becomes 2p prime minus 3p double prime plus p. So 2 times the derivative of 1 minus 3 times the second derivative of 1, those both go to 0, plus 1 equals 1. Similarly, we do that for all of them. You can check the steps if you want. Now we have to take our answer. So for the first one, we got 1, then we got 3, then we got 4x minus 5, and then we got 6x squared minus 18x plus 1. Now we have to represent those as vectors, which we know how to do, right? 1 is going to be represented as 1, 0, 0. 3 is going to be represented as 3, 0, 0. 4x minus 5 is going to be negative 5, 4, 0, right? Because negative 5 times 1 plus 4 times x is 4x minus 5, similarly like this. And then we stack them in column. So 1, 0, 0 is going to go in the first column, 3, 0, 0 in the second column, et cetera, et cetera. Okay. Let's make sure the dimensions work. Remember, we want to go from P3 to P2. P3 is 4-dimensional and P2 is 3-dimensional. So we should be able to take in a 4-dimensional vector here and output out a 3-dimensional vector, which makes sense, right? Because our matrix is 3 by 4. So we multiply by a 4 by 1, and then we get a 3 by 1. Excellent. Yeah, it looks like we did it. At least the dimensions are right. Again, that's a good way of checking your answer. Okay, any questions about, and this is just like you can test your answer. Okay, as in you could take any random vector now. So that's kind of the power, right? Now we can take any random vector, polynomial, right? Apply the transformation and make sure that the numbers check out. Okay, any questions about that process? Okay, next, there's one more specific case where you're doing transformations on matrices. So for example, let this transformation, new transformation T, be T of A. It takes in a 2 by 2 matrix A and outputs 2A minus A transpose. Okay. In this case, it's tricky because you may say, oh, our matrices are 2 by 2. So what does the transformation matrix look like? What's key to realize is, again, we have to represent everything as vectors, right? Our polynomials, 5x plus 4, we represent it as a vector, 4, 5, 0, 0, right? A matrix, A, B, C, D, we have to unfold it into its vector form. Then we can do transformations on it, okay? So we're looking for how to find MT. First step is we choose the basis. So we choose a basis for R2, 2 by 2, which is the standard one. But now we need to represent them as vectors, right? So any matrix A, B, C, D can turn into the vector A, B, C, D. Okay. Then we do the transformation to each one of these vectors in the basis. So what do? We take T of the first basis vector, right? And we know T of A is 2A minus A transpose. Let's just do it out an example for 1. T of 1, 0, 0, 0 is going to be 2 times 1, 0, 0, 0 minus the transpose of 1, 0, 0, 0, which is 1, 0, 0, 0, equivalent, right? And we do this out, we get, well, we multiply the 2 in, so we get 2, 0, 0, 0 minus 1, 0, 0, 0 gives us 1, 0, 0, 0. And then remember, we have to form that into a vector. So 1, 0, 0, 0 is the output. Okay. We do that for each one of the basis vectors, 1, 2, 3, and 4. And then we get these 4 columns here, right? So this is the first column, second column, third column, fourth column, and boom. Stack it. Okay. Another way of thinking about this problem is you can say, okay, let's say I have a random matrix A, B, C, D, and I apply T to it. So I see that A, B, C, D turns into A, 2B minus C, 2C minus B, and D. In other words, this vector right here, right? This vector right here turns into this vector right here. So now it's like a puzzle. Now basically you're starting with a vector here, and you want to turn it into this vector here, and you like fill in the, oopsies, you fill in the matrix here to make that work. This is a good way of checking your work, but like basically what you want is for like this row, let's say we didn't know, this row times this column would have to equal A, right? So the only way for that is to take 1 of A and take 0 of everything else. And just like that, you fill in the matrix. You'll get the same answer. Okay. What's next? Okay, so in linear, when we have linear transformations, they're represented by matrices, right? Now, the determinant of that matrix tells you a lot. That determinant tells you what happens to like the volume or the areas and the shapes in space. So if this is your matrix transformation, so let's just draw. It's best to see with a diagram. I think this is something you may have also learned in 1410, so this might be a little bit repetitive. But let's think about let's say before transformation. Okay, what do we have? We have our two basis vectors, 1, 0. Let's do a different color. Actually, you know what I'll do? I'll just do a big one. Okay. Okay. Our basis vectors are 1, 0, and 0, 1. Right? Now, if our matrix is this, for example, our transformation is this matrix, what does it do to the basis vector 1, 0? Well, we multiply it out and we see that it changes 1, 0 to 2, 0. Okay, so let's do another one. Change color. Okay, before transformation, let's do after transformation, right? I have in my new coordinate space, 1, 2, 3, 4, 1, 2, 3, 4, right? What happens to 1, 0? It gets shot to 2, 0, so that goes here. And then 0, 1 gets pushed to 0, 3. Now, if you notice here, the area of the shape formed by these vectors is 1. And here, the area of the shape formed by these vectors is 6. If you look at how do we go from 1 to 6, you can see that we multiply by 6. And no surprise there, this number that we multiply by is the determinant. So the determinant is the value of the determinant tells you how you scale areas in your grids, pretty much. And in 3 dimensions, that's volume. In 4 dimensions, that's something else. We don't know what it's called. Okay. So right, because the determinant is 6, so here's like the main things you really need to know. If your determinant is bigger than 1, you're stretching space out, you're making things bigger. If it's between 0 and 1, you're compressing because it's a fraction, so you're turning like an area of 1 into an area of a half or something. If it's equal to 0, then everything is collapsing onto one line. And we're going to see that has to do a lot with eigenvectors and eigenvalues. We'll see that in the next chapter, I think. Yeah, in the next chapter. And if it's less than 0, then you just have to know, like, conceptually it flips space around. It's basically we'll just like take 1, 0, right, and flip it around, turn it to the other side, and 0, 1 will come to the other side. Not as important. Okay, any questions about that, about linear transformations and determinants? No. Let's take a 3-minute break. Wait, okay, actually let's take a 5-minute break, and I think in the last 30 minutes we can finish up eigenvectors and eigenvalues. So let's come back at 5:30. If you have questions, drop them in the chat. Okay, let's come back to let's do one practice problem for whatchamacallit for linear transformations, and then let's get to eigenvectors and eigenvalues, then call it a day. All right, so let's see here. Here's our problem. Okay, so similar to this is very similar to the example we saw with just a different transformation. So it should be the same process. So we need to find the matrix of T. And it says with respect to the standard basis of P3 and P2. So basically our basis for P3, right? What did I write P? For P3 is going to be 1x, x squared, x cubed, right? And then for P2, it's going to be 1x, x squared. Right. Okay. So again, we're going from P3 to P2. So we need to take the transformation on each one of the basis elements of whatever our transformation is. So our basis is P3. So we need to take the T of 1, T of x squared, and T of x cubed. Okay. So let me choose a less bright color, maybe blue. Okay, so T of 1 is going to be 1 prime plus 1 double prime plus P of 1, correct? And if, remember, our P is 1. So our P of x in this case equals 1. So P of 1 is just going to be 1. So it's going to be 0 plus 1, so 1. Okay, and let's write this as a vector, right? Now we need to represent it in P2. So how do we write 1 as a vector in P2? That's going to be 1, 0, 0, right? 1 times this thing plus 0 times this thing plus 0 times that thing. Okay, T of x prime is 1 plus x double prime is 0 plus 1 again will give us 2. Okay, T of x squared is going to, let's just do it out. X squared prime is going to be 2x plus 2 plus 1, right? Which is going to be 2x plus 3, which is going to turn into 2, is going to be 3, 2, 0, correct? Or sorry, yeah, 2x plus 3 is 3, 2, 0, correct? And then last one is T of x cubed is going to be P prime 3x squared plus P double prime 6x plus P of 1 plus 1 again, which is going to be 1, 6, 3. And then we form matrix MT by just stacking these as columns. 1, 0, 0, 2, 0, 0, 3, 2, 0, 1, 6, 3. Okay, and the key idea here when you form matrix MT is that we have basically, if we have a matrix, all of these columns is basis of P3. Okay, so you take the basis of P3 and stack them as columns, and you multiply by MT, you should get out you multiply by MT, you should get out these the basis of P2. Okay, so that's kind of what this matrix is doing in terms of why we actually stack them in columns like that. Okay, let me get rid of that. The next problem is saying find the matrix of T with respect to a new basis. So now I'm not gonna do the whole thing out, but what we'll do is instead of dealing with our using our standard basis here, we're gonna change our basis of P3 to be something random, which they want for us, which is the kind of the tricky part. But I mean, it's just gonna be a different basis. It's gonna be the same exact process. So it's gonna be what 1 x squared x cubed 2 minus x, right? And then this basis is gonna become 1 3 plus 2x, and then 1 plus 6x plus 3x squared. Very random basis, but let's see, right? Let's do T of the first thing. So remember, basically what's going to change here, instead of 1x, x squared, and x cubed, we're just going to replace it with our new basis vector. So 1 x squared, x cubed, and 2 minus x. A little bit weird, but then we're gonna let's try applying it to let's try doing this row, for example, right? So we're gonna do T of x cubed is gonna be x cubed prime, so 3x squared plus x cubed double prime plus 3x plus 1. We already saw that, right, when we did it here before. And if you notice, this, right, in terms of this basis right here, is actually represented by 0, 0, 1. If you realize, that's why they kind of made this basis so weird, because you take 0 times this guy, so 0, 0 times this guy, and clearly 1 times this guy will give you out the output that you're looking for. Okay? All right, so enough of linear transformations. Let's go to the final chapter. There's one more practice problem for linear transformations. When you see the solutions, try those out. Okay, eigenvalues and eigenvectors. So the idea is that, like, if we just go separate here real quick, all eigenvalues and eigenvectors are, they satisfy this equation A times V equals lambda V. And it's like, I don't know what A is. I don't know what any of these things are. A is your transformation matrix. So A is a matrix, right? That's taking in a vector and it's outputting a new vector. So usually we write the vector on this side, like the output, but here the output is just going to be on the right side for now. Okay. What we say is that the output is a scaled version of the original vector. Okay. So for example, if I have some matrix A and I multiply it by 1, 1, and I get 2, 2, right? 2, 2 is the same as 2 times 1, 1. So here you would say, okay, your matrix A is A, your V is 1, 1, and then your lambda is 2. Okay, V is what we call eigenvectors. I don't know why I'm writing this, it's literally underneath. So V is called the eigenvector of A, and each eigenvector has its own eigenvalue lambda. Okay, let's try this example. We're asked, is the vector 1, 1 an eigenvector of negative 1, 3, 2, 0? If so, find the eigenvalue associated with it. So let's see if it's an eigenvector. We just do A times V, and we see if is this equal to lambda V, yes or no. So we do A, we take A, our matrix, and we multiply it by the vector, and we get 2, 2. Notice that 2, 2 is exactly a scaled version of the original, correct? So we see that AV equals lambda V, and V is going to be 1, 1, and lambda is going to be 2. So we say the terminology is that 1, 1 is an eigenvector of A with eigenvalue 2. Okay? Hopefully that makes sense. How do we generally find the eigenvectors and eigenvalues of a matrix? Well, let's think about this. If we take the equation AV equals lambda V, and we bring, let's draw vectors on it to make it clear. Bring everything to one side, and we factor out the V. So we get A minus lambda. I'm going to put the identity matrix in there. The reason we put the identity matrix in there is you can think of it as like 1. It doesn't actually, it's just like lambda times 1. But we put the identity in there because A is a 3 by 3 matrix. Oh, no, not a 3. And A is a matrix. It doesn't have to be 3 by 3. Sorry. A can be any matrix. But lambda on its own is just a number. So we multiply it by the identity to like make this matrix subtraction work. Right? Anyways, equals 0. Okay. Does this ring a bell? This looks like this expression is the equivalent of saying V is in the kernel of what matrix? Of not A, but A minus lambda I, right? We're saying A minus lambda I times V equals 0. So V is in the kernel of A minus lambda I. And that means that A minus lambda I has a kernel. And if you remember from that chart we did in like chapter 3, if a matrix A, if a matrix has a kernel, right? Then determinant is equal to 0. So we know that because this matrix right here has a kernel, that the determinant of this matrix, A minus lambda I, must be equal to 0. And this is the key equation you have to remember. So it should be down here a little bit. Boom. We get that determinant of A minus lambda I equals 0. That's how we're going to solve for eigenvalues. Okay? So the steps are, given a matrix A, you first solve determinant of A minus lambda I equals 0. You set it equal to 0 and solve for lambda. Then to find eigenvectors for each lambda, you solve A minus lambda I times V equals 0 for the specific V. Let's do an example. So here's our matrix. We want to find eigenvalues and eigenvectors. Again, we want to find vectors such that when we multiply this matrix by them, we end up with a scaled version of our original vector. That's what we're looking to do. Okay, and that's a way you can also check your work. So the first thing we do is determinant of A minus lambda I. So we first have to find A minus lambda I. So here's A. That's not A. Here's A. Here's what happens when you do lambda I, right? We take lambda and multiply it by the identity, right? Just puts lambdas on the diagonal. And then we get A minus lambda I is this guy. We find its determinant. So you guys actually, we didn't even go over how to do determinants, but you would like expand about one row, right? You would do 1 minus lambda times this, determinant of this, plus, I don't know what this guy is doing. Oh, plus 0 to this, and then plus 2 times that. Hopefully you guys know how to find the determinant, and you get this, okay? This is also commonly called the characteristic polynomial. So the determinant of a minus lambda I is usually called the characteristic polynomial of a. Right? It's a function of lambda. It looks like this. We set it equal to 0. We factor it, and we get 3 eigenvalues. Lambda equals 1, lambda equals -1, and lambda equals 3. Those are our 3 eigenvalues. Now the question is, for each eigenvalue, we're going to have an eigenvector. How do we find it? Okay, let's do it for the first one first. Lambda equals 1. We need to solve. So step 1, we found lambdas, right? Step 2, for each lambda, solve a minus lambda I times v equals 0. And then that v that you get out is going to be your eigenvector for that specific lambda. Let's do for lambda equals 1 first. We're going to do a minus, lambda is 1, so a minus is 1 times I. So a minus the identity gives us this matrix. Okay, and we go to reducer echelon form. Okay, this is very good because look, it's kind of weird. Row reducer echelon form is not the identity. Usually that is like, oh, I don't want to deal with that. When finding eigenvectors, we need it to not be the identity. Why? Because we need a minus I times v to equal 0. We need this guy times some vector v, let's call v x1, x2, x3, to equal 0, right? And that's only going to happen if, right, if this bottom row like being all zeros gives us like a kernel, gives us a null space, right? So how do we solve it? We've done this before. Let's just do it real quick. We'll say x1 equals 0, x2 equals 0, and then x3 can be whatever it wants. Okay, t can be any number. You can choose any vector you want of these. Usually it's common just to choose like 1 for t. So an eigenvector for lambda equals 1 is 0, 0, 1. Okay, and you can always go up and check this in the matrix, but if you do this matrix times by 0, 0, 1, what do we get? 0, 0, we get, oh, wait, 2? Maybe something might be wrong here with this, a little bit weird. The reduced row echelon form, x1, x2, x3, x1 is 0, x2 is 0, and x3 is 1. Oh, sorry, not a minus, it should be 0, 0, 1 is an eigenvector. Wait, am I crazy? 1 times 0 plus 0 times 0, so 2, 2, 0, 0. Okay, that's a little bit weird, but I'll clarify that at the end. Either way, the process is the same. Maybe we made a little bit of algebra mistake somewhere. Maybe the characteristic polynomial is wrong potentially. Let's see. Either way, the steps are important. So we get lambda equals 1, we get the eigenvector. For lambda equals -1, we do the same process, but instead of it's a minus lambda I, right? So now lambda is -1, so that's a plus I. We row reduce. We again get a row of zeros, which is good because that means we have a kernel. Here, a vector in the kernel is -1, 0, 1. Hopefully at this point, finding the kernel should be like straightforward-ish. So this should come naturally. And then you find 3 vectors in the kernel, and those are your eigenvalues and eigenvectors. So you get your eigenvalues are 1, -1, 3, and then your eigenvectors are 0, 0, 1, -1, 0, 1, and -1, 0, 1, which is also okay. These two shouldn't be the same. Okay, I think the algebra here is a bit wrong, but the steps are there. I'll fix the algebra here. Okay, the two important terms are algebraic multiplicity and geometric multiplicity. Algebraic multiplicity is the power that you take an eigenvalue to in the characteristic polynomial. So in our example, we had the characteristic polynomial equals lambda minus 1 to the first plus times lambda plus times lambda minus 3 to the first, right? Everything is to the first power. So the algebraic multiplicity of each eigenvalue is 1. Okay, if, for example, the polynomial looked like this, then lambda equals 2 would have an algebraic multiplicity of 3, and lambda equals 4 would have an algebraic multiplicity of 2. Okay, the Geometric multiplicity is when we solve for the null space. It's basically how many vectors are in the kernel of a minus lambda I times v equals 0. So here, assuming that we did it right, the math right, we get one vector here, one vector here, and one vector here. So the geometric multiplicity of each eigenvalue would be 1 as well. Okay? Hopefully those terms make sense. Now, why are we doing all this? One reason is so we can do diagonalization on a matrix. So diagonalizing a matrix basically means you take an original matrix A, it can look like anything. Okay. Okay. You take a matrix A, okay? It can be any type of matrix, whatever. You write it as P D P inverse, where D is a diagonal matrix. So it looks like this, and it has eigenvalues all along the diagonal and zeros everywhere else. So an example of a diagonal matrix is like this right here, right? 1, -1, 3, and then zeros everywhere else. Okay. We saw diagonal matrices as well, right? Before. And P is a matrix that has the eigenvectors stacked as columns. So like eigenvector 1 is the first column, eigenvector 2 is the second column, etc. Okay, all the way up to eigenvector n. So like if I don't know if it's clear to see, you can think about it like eigenvector 1, eigenvector. They just stack them in the columns, the eigenvectors. It's important that the order must correspond. So in D, lambda 1 comes first, then lambda 2, etc. So in P, you must put the V corresponding to lambda 1 first, then the V corresponding to lambda 2 next, and that's how this matrix multiplication will work. Okay? So an example is this. I think this was the same. Yeah, we know from before, let's assume I don't know, the math works out. If the math was right, we would find our eigenvalues, put them in the diagonal, that's D. To find P, you stack the eigenvectors, right? And then you should be able to write A right here as P, D, P inverse, right? And this matrix multiplication will work always. I don't think it'll work in our case because the matrices are a little bit off, but that's the idea. Okay. For a matrix to be diagonalizable, the algebraic multiplicity and geometric multiplicity must be equal for all the eigenvalues. So if you thought about our example before, for lambda equals 1, right? Algebraic multiplicity was 1, geometric multiplicity was 1. Good. For lambda equals -1, same thing. Good. For lambda equals 3, they were both 1, right? So good. So that's why we're diagonalizable. There's going to be a case where the algebraic multiplicity and the geometric multiplicity might be different. Sometimes this algebraic multiplicity is bigger than the geometric multiplicity. And that's a whole nother, that has like genuinely, it has its own chapter. We'll start with that next time. Okay. The question is, I mean, like one thing you might be curious about is where does this A equals PDP inverse come from? It's basically, actually, this part explains it, but basically what you're doing, if you take this equation and multiply on the right by both sides, you get AP equals PD, or AP equals DP, right? And what this is it's the same thing as AV equals lambda V, where instead of lambda, you have your diagonal matrix, which contains all the lambdas. Instead of V, you have your P matrix, which contains all the V's. So it's like doing AV equals lambda V just for every like eigenvalue and eigenvector all at once. Okay. This is just a thought exercise that's less important. Here are some important properties. Okay. This is kind of why diagonalization is nice. So if you think about it, if you have a matrix A, okay, and you're able to write it as PDP inverse, then A to the n, okay, is given by P D to the n P inverse. This means that if I have a matrix, like a big matrix, whatever, 5 by 5 matrix, right, and I want to take it to the 10th power, that's a whole lot of matrix multiplication. That's going to take forever, no? What we could do is diagonalize it and write it as P times a nice diagonal matrix times P inverse, right? And then all we have to do is take that diagonal matrix to the 10th power. And if you think about taking a diagonal matrix multiplied by itself, right? If you square this, it's very clear that the result is going to be you just square each diagonal term. So 4, 9, 4. That's a nice property of diagonal matrices. So that's kind of why it's easy to do that. And then you can just multiply by p inverse here and multiply by p and then get out your original power, which is nice. Okay, that's a nice like technique. That's kind of why. The determinant of A and the determinant of D are the same. The trace of A and the trace of D are also equivalent. The determinants are equal to the you multiply eigenvalues, and the trace is the sum of eigenvalues. Okay, that's just a neat trick. If you do some examples, you can show that, but it's just like a nice trick to know, and it's a good property that they can test you on. Lastly, again, so one more time, if the algebraic multiplicity and geometric multiplicity for an eigenvalue is not the same, then the matrix is not going to be diagonalizable like this. It's not going to have a form PDP inverse. It's going to have a slightly different form called Jordan canonical form. And we'll talk about this in the next chapter. But if you want to like read ahead before next week, then you can like kind of get the basis. Like, why are we doing this whole next chapter? It's solely because sometimes algebraic multiplicity is not equal to geometric multiplicity. Okay. Here are practice problems. Let's let's skip these for now, and we have like 10 or so minutes, so maybe now we just answer questions. If there are any questions about anything that we've done, any problems you want to revisit, or concepts that are like not making sense, just drop them in the chat, because I'm sure there's like something that didn't make sense in that like bombarding of material. Oh, also this matrix here. Oh, it's a little bit different. Okay, if there's no questions, I guess we can diagonalize this in the meanwhile with 8 minutes left. But let's actually do that because we haven't really done anything with determinants or eigenvalues. So right, to diagonalize, we need to find P, we need to find D. So to find P, we need eigenvectors, and to find D, we need eigenvalues. So we first need to find determinant of A minus lambda I. So determinant of A is going to be this guy minus lambda 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 0 0 0 0 0 0 is going to be 1 minus lambda 0 2 0 1 minus lambda 0 2 0 1 minus lambda. Okay, let's go about, I guess, let's go about the middle row. How about that? Because that only has that has two zeros in it. So let's be a little bit smart. So remember the signs for determinants go plus, minus, plus, minus, plus, minus, plus, minus, plus. So it's going to be minus 0 times that, all good, plus 1 minus lambda times the determinant of what's remaining. So what's remaining after we get these two away is 1 minus lambda, 2, 2. And we want this to be equal to 0. So 1 minus lambda times 1 minus lambda squared minus 4 equals 0. Let's make sure we do the math right there. Okay. And then this can be factored into like 1 minus lambda times 1 minus lambda minus 2 times 1 minus lambda plus 2. Hopefully you guys remember that like a squared minus b squared is a minus b times a plus b. So we get 1 minus lambda times negative 1 minus lambda times 3 minus lambda equals 0. And we can even pull out the negative or whatever. We get lambda equals 1, lambda equals negative 1, and lambda equals 3. Okay, those are our three eigenvalues. Maybe this was supposed to be like what the example problem was. Maybe the solution for the example problem is this solution. We'll see. We'll figure it out. Okay, and let's clear the work. So we got 1, negative 1, and 3. So we have lambda equals 1, lambda equals negative 1, and lambda equals 3. Let's do lambda equals 1 first, right? We do a minus lambda I, which is just going to be a minus I, which is going to be 0, 0, 2, 0, 0, 0, 2, 0, 1. Okay, let's turn it into reducer echelon form. We can bring this guy up to the top and like divide by, bring this row up to the top and divide by 2, so 1, 0, 1/2. And then bring this row down and divide it by 2 as well, and then bring the row 0 to the bottom. Okay, so clearly x3 is free. Let's see, so times x1, x2, x3 has to equal 0. Right, remember we're solving for a minus lambda I times v equals 0. So we get equals 0. So we get x1 plus 1/2 x3 equals 0. We get that x3 has to equal 0, and x2 looks to be free. So let's let x2 equals 1, right? x2 can be 1, whatever, it's free. So x2 could be 1, and then x3 has to be 0, and if x3 is 0, then x1 also has to be 0. So 0, 1, 0 is eigenvector for lambda equals 1. Okay, just like that. See, I guess we can finish it up. Lambda equals -1 is going to be a plus I here, right? So 2, 0, 2, 0, 2, 0, 2, 0, 2. These rows are redundant, right? So I'll just turn this one into a whole row of zeros and then divide this one by 1. So I get 1, 0, 1 and 0, 1, 0. I don't know if that makes any sense. Let's just say 1, 0, 1, 0, 1, 0, 0, 0, 0, right? Again, times x1, x2, x3 equals 0. Let's clear some space here. What does this say? So this says x1 plus x3 has to equal 0, x2 has to equal 0, and then x3 is free, looks like. So x3, let's call it 1, let's call x2 0, and then x1 has to be -1, right? Because if x1 plus x3 equals 0 and x3 is 1, then x1 has to be -1. So x1 is -1, x2 is 0, x3 is 1. That's a vector. So for lambda equals 1, we found this one. For lambda equals -1, we find this one. Okay, last one. It's a bit extensive. Lambda equals 3. A minus 3I equals, you're just going to subtract 3 along the diagonal. So -2, 0, 2, 0, -2, 0, 2, 0, -2. Let's see which row we get rid of this. So let's first divide these two rows by 1, maybe, -1. Divide this by -1. So we get 1, 0, -1. Divide this by -1, we get 0, 1, 0. And then this one might as well also divide by -1 and get 1, 0, -1, which is going to just cancel out with the top row and turn 0, 0, 0, right? And so one more time, times x1, x2, x3 equals 0, 0, 0. That gives us out x1 minus x3 equals 0, x2 equals 0, and x3 is free. x3 can be whatever it wants to be. So x3, let's call it 1. If x3 is 1, then x1 is also 1 because x1 minus 1 equals 0. So 1, 0, 1 is our vector here. Okay, now that's done. Let's erase what we have here to form PD. Actually, I can do this. Take this whole thing out. Okay, finally, let's box our important information here. This guy and this guy. So now we're gonna write A. So A is 1, 0, 2, 0, 1, 0, 2, 0, 1. A equals P. So P is gonna be this guy stacked, is gonna be the eigenvector stacked in order. So we're gonna do lambda equals 1 first, then lambda equals -1, then lambda equals 3. So P, and then D, we need to do the order, right? Lambda equals 1 first, then lambda equals -1, then lambda equals 3. And D is going to be a diagonal matrix. And then P inverse, which we don't really have to compute usually. Oh, sorry. Yeah. So P equals and then P inverse. One last thing before we go, I forgot to mention this, is that if you look at the problem, it actually says, what am I writing? Sorry, we want P inverse here. 0, 1, 0, -1, 0, 1, and 1, 0, 1 inverse. Okay, so the order is a little bit tricky, so write it on your cheat sheet. A is equal to P dP inverse. If we, let me make some space. If A is equal to P dP inverse, if we multiply on the right by P and on the left by P inverse, multiply on the right by P and on the left by P inverse, these will cancel out because identity, and these will cancel out because identity. So we get P inverse AP equals D. So that's another representation of the same equation. So here it's asking for P and D such that D equals P inverse AP. It's the same idea. It's basically just asking for P and D, and you can rewrite it however you want. Okay. All right. It's 6 p.m. So I saw something in the chat. Oh, it's probably about the math. Wait, let's see. Did I make a math error?
Yeah,
Shouldn't
we're doing lambda equals 1, A minus the identity matrix.
Okay, so that goes to show that like do this enough where you don't make math errors because that's annoying. It's the okay, like last I guess tips about the placement test. Um it's gonna be pretty computation heavy and like obviously show your work, you'll get partial credit, but you should be able to like there's like for each chapter there's like 3 or 4 classic problems that you need to know how to solve and like get them all the time. If you do that, then you should be able to pass the placement. There's gonna be like 9 problems. One of them 1 or 2 might be a little bit funky, but like 7 are going to be consistently the same thing every single time. So yeah, any final questions? Any questions about anything that we did today? There's a lot of material. Hopefully we'll get the solutions up to these soon and I'll fix the whatever issue is going on in there. I'll take a look at it. Yeah. Oh, question. I want to place out a math 1410 and 2400 so that the first math course is 2410. Do I need to pass? Okay, no, I think I know of someone who went into 2410 without having passed placement for 2400. So I think with Penn Math, they're very lenient with the prereqs in terms of like letting you take a course, but like just make sure you're prepared for it. Um, I think you should be able to register for 2410 either way. It won't block you. And if you're in Path and it's letting you register for 2410 without any warnings or anything, then it's probably gonna let you register. But just make sure like you do feel confident in 1410 and 2400. You could probably just split it up and take 1410 placement this upcoming fall and then 2400 placement the next spring or something. Or if they let you take both at once, you can do that.
Yeah, you shouldn't have any restriction to signing up, like what Autumn said. The only thing is though that 1410 less than 2400 is like just like different. Like volume 4 of 1410, I don't think is taught at any like in any multi-class typically. So I would just like look over some things.
Yeah, make sure you prepare properly with like the material that we have will help. More questions. Yes, these are gonna be recorded. So no worries if you can't make next week. If you have any questions about like obviously there's some errors in the notes, like we just wrote them. So always email, like just email me. If you have a question about like how we got a solution, just email me. I'll get back to you as soon as possible. But yeah, we're gonna record next week's as well.
They're under the class recordings tab of Canvas. It'll be uploaded like maybe like 3 or 4 hours after the session once Canvas processes them.
All right, any other questions? Otherwise, we should be good. Next week is going to be a lot like the harder material is going to be next week. But hopefully like at this point like the foundations are there so it'll like the intuition. So that's what I would suggest maybe before next week like come through having at least skimmed over like session 2 notes. We'll post those soon. Just so it like can like click more. Because to do this all in 6 hours is like a lot of material. Yeah. But anyways, thank you guys.
Thank you guys. See you next week.
Thank you guys for coming.
Bye.
All right, I'll see you guys next week, Adam and Mahima. Great.
All right.
As always, Adam.
Thank you for
Bye-bye.
all the work, Adam.
No problem. No problem. See ya.
Yeah, bye-bye.
Bye.